of cations, and those that are inclined to the formation of anions, we are calling non-metals. And those that kind of behave as if they can lose, as if they cannot lose. These are the metalloids. And so if we consider the general form, I think the last time we went through this, three of us. Did we go through that? Okay. Can somebody help me if we, so that I don't repeat myself? Okay. I don't know if your silence means consent or I don't know. Well, let me take it from that point again. So we or what we are trying to say is that we have these elements that can release electron and become positively charged. And these are what we call metals. Of course, they can combine with other metals to form a mixture of metals. That mixture of metals is what we call alloys. And so we have pure metals, we have alloys. That's a combination of metals. Of course, metals can also combine with non-metals to form the ionic kind of compounds, or it can combine with the semi-metals or the metalloids. That's what we are calling the semiconductors. So we'll see these metals as I'm showing here. Some of them are in the alloy form. Now, for example, when we take brass, then we are looking at brass to be a combination of copper and then zinc. That's what we call brass. But if I take copper and tin, then I'm looking at, so if this is brass and then this is bronze, then I'm looking at copper, a little bit of copper, and then tin. Then I have steel. Well, when we have much percentage of carbon in there, it becomes a stainless steel. And then we have a steel which is made up of iron, carbon, manganese, and small amount of silicon, that's sand, silicon oxide, phosphorus, and sulfur. That's what we call steel. And then we can have them in their pure kind of form. So metals in general, because we know they release electrons, are quite active when it comes to conductivity. So they are both good conductors of heat and that of electricity. So they are electrically high conductive, and then thermally they are also conductive. And we mentioned the general properties of these metals. We see they are quite malleable, they are ductile, they usually can be pulled into wires and can be broken down or can be hammered down into quite some pieces. I think the last time we tried to look at that, but the course we try to restrict ourselves to the main group element, where we look at the group 1 element, the group 2 element. Please, it looks like I went through this with you, so I've gone too far. Please, can you confirm? So there's no good Samaritan there to confirm. Am I off? Let me check.
Yes,
I
please.
I went through with you, right?
Please.
Yes or no?
Yes, please.
Yes.
So where did we end? So I don't go back. Can somebody tell me where we ended the last time? Did we go through the general kind of properties of these metals where I consider the group 1 metals, group 2 metals, and group 3 metals, and those that are left like the germanium, indium, tin, lead? We look at that. So I mean, this particular pictures, did I go through with you?
We went through with this one.
So it means that we went through all this one. So then I remember it was time to start the whole thing, right?
Mm.
So I think this is where we're supposed to start from, not like going back.
Yes, please.
Yes, sir.
Uh-huh. Okay, thank you very much.
Oh, you're
Welcome.
welcome,
I
sir.
was asking the course rep, but then I didn't hear from him. So this is where I'm supposed to be starting from, not to go to. Okay, but we've gone through the general properties of these. I mean the group one, the alkali metals, which is the group one. That's the ash kind of metals. Now we understand that the group one consists of the lithium, sodium, potassium, beryllium, cesium, and then francium. In general terms, we know lithium much because of its properties, which helps us to use them in batteries. So lithium batteries, we see them a lot. So the cell batteries that we know, sodium, and of course, sodium, potassium, we get to have them in their salt form, like the common salt, the rock salts that have. Now, these elements will engage water, and when they engage water, they want to be much vigorous when they are reacting. So group one metals, of course, they react with water, but then in a vigorous way. So we should just know that. And of course, we also know that they are very soft, like lithium. You can easily cut lithium with knife. So it makes the group one metals, we can place a group one metals to the point where they can easily release that one electron and become positively charged one metal. So if you are looking at their general properties, then we'll say that the alkali kind of properties makes them shiny gray, ash. Alkali means ash. So it will make them shiny gray, and they are very soft. Just as I said, you can even cut some of them with knife. Well, if you look at them and we compare them to water, we'll try to say that some of them are quite less dense than water. Well, they'll be good conductors of heat and then electricity. But then if you move down the group, then you'll be, of course, reducing the nuclear effects, and then you'll be increasing the nuclear effect, meaning you would rather be moving more to having more a boiling point and of course high melting point or in that kind of way. Well, again, as you move down the group, then you're increasing the reactivity. I think the last time we tried to explain that as well. Now let's look at their general properties. I mean, their general chemical reactions, so that when I take them one by one, it will to follow the general kind of reactions there. So I look at some common general reactions of the group one metals. Well, I can put them in this form. The reactions with oxygen, reaction with water, reaction with hydrogen, reaction with halogens, acids, and then ammonia for that's a base. And then the reaction which we form the ionic kind of compounds, general reactions with these non-metals to form ionic compounds. And then they also react with some organic compounds as well, just because they have that positive charge. So if that organic compound, which now becomes a ligand, also have its negative parts, then it can react. Now let me switch to my writing part so I can just show you the general reactions of them. So sorry. So um, I hope you can see my whiteboard.
Yes,
Okay.
please.
Yeah, so I'm taking them one by one. So reaction with oxygen, I'm giving you just a general kind of formula or the general kind of rule, so you can be able to predict in case we bring a real kind of a situation in there, we can predict. Now, I use M plus to represent the group 1 metal. So they have just plus 1. So when we get to the group 2, we'll put 2 plus. Okay, so it means that the M plus can be lithium, it can be sodium, it can be potassium, it can be rubidium, cesium. Of course, as you are getting to the radioactive, we have not really engaged them, but we know theoretically they can follow the same kind of procedure, I mean the same reaction procedure. Okay, so if I take reaction with oxygen, so I'm looking at the reactions with oxygen. Of course, we can have 3 forms of oxygen. When we come to the non-metals, it will just be like treating it the same way. So we can have what we call oxides. We can have the peroxides and then the superoxide. So we have 3 forms of oxygen: the peroxide, the superoxide, and then the oxide itself. The most stable of these oxide is the normal oxide that we have. So note that. That's why we usually see oxygen to be having the -2, but it can also have the -1. This is what we call the peroxide. The example is hydrogen peroxide. So in this case, the oxidation state of the oxygen there is -1. Okay. Then we have the superoxide. So like calcium oxide here, we are having the charge to be not, this will be -2. But then if we have, say, sodium 2 plus O, then basically we are looking at it as having the oxide its form. So please note that we have 3 forms of oxygen in the oxidation form. We have the oxides, we have the peroxides, okay, and then we have the superoxides. And the oxidation form is what I have written there. So the oxide will have O, which is -2. Peroxide will have O -1. Then the superoxide will have a -1. Okay, so that's with that background, I can now look at how the metals can be reacting. So it means that the +1 metals can react with the molecular oxygen to produce oxides, metal oxides. Now, the metal oxide can be in 3 forms. It can produce the metal oxide, okay? It can produce the metal peroxide, which is M2O2, and it can also produce the metal superoxide, that is MO2. Is that okay?
Yes, Doc.
What's happening?
Hello.
Hello?
Hi,
Oh,
Doc.
sorry.
Hello, Doc.
Sorry, I muted it. Yes. So we can have reactions with these alkali metals, when it reacts with oxygen, we can have it in these three forms. We can have the metal oxide, the metal peroxide, the metal superoxide. We can cite example. So for example, if lithium, so let me cite example. Yeah. Okay, so so if I have lithium reacting with oxygen, then I'm going to be forming, for example, lithium oxide. Okay. If I have, say, for example, sodium reacting with oxygen, then I can form sodium oxide or sodium peroxide. Is that okay? Then if I have, say, for example, potassium, we can form so potassium reacting with oxygen, we can form the potassium oxide, potassium peroxide, and potassium superoxide. Now, if you notice, it means that as we go down the group, then the reaction with oxygen begins changing. So the trend will be, as we go down the group, the metals can be reacting with oxygen to form the oxides. Then it will tend to reduce to react to form peroxide, and then the superoxide, because of the atomic sizes and then the ionization kind of stabilization. So what it means is that it's only lithium that can form oxide in the group 1. So lithium will form a stable reaction or oxide with oxygen. Now potassium will also form a stable reaction with oxygen to form the peroxide. Now, as you are going down, potassium, rubidium, cesium, again, francium, we have not engaged that, but we know it can follow the same trend. And that will react to also produce the most stable one will be the superoxide. Yes, the superoxide. So we have the oxide for lithium being stable, the peroxide, superoxide from potassium coming down. Is that okay? So lithium, if you take lithium, potassium, what are the elements there? Rubidium, cesium, and then francium. So means that as you are going down the group, so lithium only forms the oxide, then it cannot react with oxygen to form the peroxide, but sodium can form the oxide and also form the react to form peroxide. Now potassium can react with oxygen to form the oxides, the peroxide, and then superoxide. So as we are going down the group, we'll see that will form starting from potassium, we can have the superoxide formation as well. So that's a reaction with oxygen. Any question? I want to clean my board, so if you have a question you want to ask.
No, please.
Okay. Yeah, so then we'll look at the reactions with water. So so the next one, we consider the reactions with water. So if I want to bring my board back, then it means that I want to react M1 plus water. Can somebody predict what will be the product? What do you think will be the product? Yes. Joseph, I thought you are from me. Yes, talk. Okay. So metal reaction, or the group 1 metal reacting with water, will produce the hydroxide, metal hydroxide, and then to release hydrogen gas. So that means that I can produce metal hydroxide. I can produce metal hydroxide, sorry, and then hydrogen gas will be released. Okay, so of course, I'm not balancing the equations here. We can try to balance it, and that you are not interested in stoichiometry. So 2 moles here, 2 moles here, and that 2 moles, so that the hydrogen gas will be balanced. So reaction of group 1 metals with the water will be producing a metal hydroxide, and then hydrogen gas will be released. Are we okay? So we can cite example. So we can cite example, say for example, sodium ion reacting with water will produce sodium hydroxide, and then hydrogen gas will be released. So the arrow pointing up basically means hydrogen gas is just going to be released. Is that okay?
Yes, sir.
Yes, doctor.
Okay.
So,
Yes.
hello, sir.
Yes, sir.
So, sir, is it possible that when the sodium reacts with water, you get sodium oxide and then, or it is always hydroxide?
Sodium hydroxide. With water, you produce hydroxide, not oxides.
Oh, okay.
It's only when it reacts with oxygen that you produce the oxides. But with water, you are producing the hydroxides, and then hydrogen gas will be evolving from that. But in terms of this experiment, when you want to do such experiment, we do that with all caution. So for example, lithium can gently react with water. But then as you are going down the group, then their gentility will begin increasing, decreasing. So they'll begin reacting with water vigorously. I don't know if you have used sodium hydroxide before. So if you are dissolving sodium hydroxide, you feel from the bottle that it's quite hot. I don't know if you have done that before. So sodium and water don't really agree at all. But then as you are going, then it's even quite dangerous, because even for potassium, metallic potassium, it's even can start, it can ignite a flame. For rubidium, cesium, it will just explode. Okay, so when you are dealing with such a reaction, we do that under control, but then it will react, although when it's being controlled, to produce a hydroxide, and then you see the hydrogen gas evolving from that. Is that okay? Well, the next is to look at the reaction with hydrogen. Okay, so reaction with hydrogen, I guess somebody can help us predict that. So a metal, the group 1 metals react with hydrogen gas. Can someone predict what the product will be?
Hydride.
Hydride.
I think it will produce hydride.
Metal hydride. So metal
Metal
hydride. If you want
hydride,
to balance the equation, that's this balance equation. So it will produce a metal hydride. And of course, the hydride there is just telling you hydrogen becoming a negative charge. When hydrogen is positive, that's a proton, and when it's negative, that's hydride. So now we are having an ionic compound there. And this metal hydride also, if you engage them with water, they become vigorous, and then they will just release hydrogen gas. So if I engage this metal hydride with water, so it's going to be producing the hydrogen gas in a vigorous way, and then it will release my my metal. So that's just that. So the prediction of hydrogen reaction with reaction of the group 1 with the hydrogen gas will produce metal hydride. So it means that we can also predict when it is high, the halide. So let me put S2 here, representing halide. Halides are the halogens. So reaction with the halogens. So we can easily predict this and know we are going to be producing metal what?
Metal halide.
Metal halide. We're going to produce metal halide. So for example, potassium reacting with, say, chlorine gas, we're going to produce potassium chloride. That's metal halides. Sodium reacting with chlorine will produce sodium chloride, which we call the common salt. Are you okay? And again, we should note that as we are going down the group, reactivity is going to be increasing. So their reaction will quite be vigorous. Now, another reaction which we can mention, I don't know if somebody is asking a question, is so I've done for hydrogen,
Sir,
I've done for,
sir, a
yes,
question.
yes.
So, sir, assuming you asked a question on the why hydrogen can react with the other group one, though hydrogen is also in group one, you can react with group one element, but other elements in group one cannot react with each other. What would be the best explanation to give?
It's let me correct.
Please do get my question.
Yes, I get you, but let me correct it. Hydrogen is not in group one. Hydrogen is placed under group one, does not make it belong to group one. Hydrogen can be placed in group 7.
Yes.
And that's because it has 1 electron in the valence share. Hydrogen can lose and behave like group 1, but then it does not make it a metal. Now, because it has that 1 electron in the valence share, it can also accept an electron and behave like the halogen. So we can also put hydrogen in the halogen group. So some periodic table will put it in the middle so that you know it doesn't belong to any group. So it behaves like them, does not make it like like them. So we put hydrogen in group 1 because it's behaving like the group 1 will be behaving, but then it is not a metal. We put it under halogen because it can behave like the halogen, does not make it a halogen. So we should clear that. Number 2, the metals in the groups can react with themselves. And that is what we call alloys. So they can be combined and form a mixture of alloys. So if you say they cannot react, and they do that using the metallic bonding. So I want to clear that kind of notion that the metals don't react with themselves. So having said that, now come clear with your question again.
Sir, please, it's okay. I think it's okay.
Okay.
So, sir, please. So if they ask to write maybe group 1 element, maybe 5 group 1 element, and you write oxygen, hydrogen, will it be marked for you or it
you
will
are
not?
wrong.
You are wrong.
You are wrong.
Okay.
Wrong.
Yeah.
Okay, sir.
Okay. Let's proceed then. So we can look at the reaction with acids and then bases. So I'll just also clean my board again, and then see the reaction with acids and then the reaction with bases. So let's start with the reaction with acid. Let's take, for example, an acid like the HCl, hydrochloric acid. So the group 1 metal reacting with HCl. Can we predict what will be the product? What do you think will be the product?
It is one metallic salt and hydrogen gas.
So we'll form the halide, metal halide. So the metal chloride and then the hydrogen gas. So it means that if I have a binary acid, what it means is that I'm going to form a salt and a gas evolving. So what do you think when it is sulfuric acid? When it's sulfuric acid, what happens?
You also form a salt and hydrogen gas.
So the metal sulfate, which is a salt,
Yes, please.
plus a hydrogen gas.
Yes.
Hydrogen gas evolving from that. So note that when the group 1 metals react with acids, it vigorously releases hydrogen gas, and what is left will be the aqueous salt left. Is that okay? I said vigorous because such reactions are very vigorous, especially if we are dealing with concentrated kind of acids. If you don't take time, it can break the bottle. If the bottle is not a Perez kind of like a beaker you are using, and it's not a Perez reinforced glass, it will crack it. Okay. Now, reaction with a base, and that base we take, say, for example, ammonia. Okay. So when we take ammonia, for example, so metal reacting with ammonia, that's a weak
produce
base.
ammonium salt.
It will produce. Come again. What did you say?
Ammonium salt.
What do you mean by ammonium salt? So I get you, but then that's not ammonium salt. Is NH4, then a salt. That's what you call ammonium. But if you look at the equation, we can't get NH4. So it's rather going to be producing a metal amide. So NH2, and then hydrogen gas will be released. So that's metal amide. So this is an organic compound. The amide is an organic compound. So we have amide. So when a group 1 metals react to that to form a metal amide, we can cite an example. For example, sodium drop in ammonia. You have this pungent smell coming out, and that is the metal amide which has been formed.
Okay.
It changes to a blue, kind of a deep blue solution. Okay, so that is with a weak kind of a base. Now, what happens if it is a strong base? So a metal, a group 1 metal reacting with a strong base. Can you predict what you think will happen? Yes, what do you think will happen? But definitely we are going to be forming just a metal hydroxide. That's okay. Okay.
So, sir, hello.
So, yes.
So, sir, assuming you are reacting sodium hydroxide with a metal, group one metal, because sodium hydroxide is also a base. You have two metals.
So what it means that, let's cite the example. So let's assume we are reacting lithium with sodium hydroxide. What do you think will happen?
To produce lithium hydroxide,
There'll be no reaction. Tell me why. Why there will be no reaction?
Hello, sir.
Yes.
Please, come again. I didn't hear what you said. Please.
We are citing an example of whether if you are reacting a base like sodium hydroxide with and I'm citing examples of them. Like, for example, lithium reacting or we dissolve sodium hydroxide so that we can have the base of that, and then we drop in lithium. What is going to be happening? I'm saying that there'll be no reaction, and I'm asking why. Yes.
There wouldn't be any reaction because lithium is +1, sodium is -1. So that is my
Oh,
understanding.
no, please. Don't confuse yourself. Sodium is also +1. I thought you were going from a different angle. They are all in the same group. So hydroxide is a -1, then the sodium is +1, lithium will also be +1. But why would there not be any reaction? How do we, yes, somebody talking. This is a single displacement. So sodium is less reactive than, lithium is less reactive than sodium. So there's no way lithium can displace sodium. So there'll be no reaction. However, if I should go down there and then I pick, say, for example, cesium, that's my, okay, so I pick, say cesium put in sodium hydroxide solution, then definitely I'm expecting to be forming cesium hydroxide and then the sodium still moving. And of course, this is still aqueous though, but then the solution will be more cesium hydroxide than sodium hydroxide. So it still forms the hydroxide of that metal. And now because cesium is much reactive than sodium, it can displace that. That's a single displacement reaction.
Yeah. Hello, sir.
Yes, sir.
Yeah, please. I thought as, but when you look at, I think some of the books, with the reactivity series, they place lithium ahead of sodium. That's meaning lithium reacts more than is more reactive than the sodium.
I'm yet to see what you are trying. So in terms of what, in reacting with what, that I think the last time we tried to explain what reactivity is. So and we give some terms to the reactivity. Is that true? Let me find out. So I don't know.
So
What yes. Let me minimize this and then take you back. So we can.
So
Yeah. So you remember this slide? Please, you remember I think we mentioned this before. Okay, so I'm yet to see in terms of what will lithium be much reactive than sodium. I'm yet to see that. And what do they give to that? Okay, so that's my listen. Okay, so maybe you show us their explanations to why they are saying sodium is right. But as far as I know, lithium cannot be reactive than sodium. So there's no way lithium can displace sodium. And of course, we can try that in the lab as well. So we have sodium hydroxide solution, drop in a sodium metal and see if there will be something going on.
Hello, sir.
Okay. Yes.
So I think some few minutes ago you explained that the group 1 metals, they react among themselves. So I am a bit confused. Come again.
They form alloys. They form alloys, a mixture of metals.
Yeah, so they form alloy. So I am looking at it that if lithium and then sodium, though sodium is more reactive than lithium per the explanation that you gave us right now, why is that they cannot form an alloy so that the hydroxide will detach?
Okay, thank you. Look at it. Always when we're talking of reactivity, please note that when we have oxidation state of 0, that is the metallic form. And then we have when the metal or the element is charged, it's different from when it is not charged. So when we're talking of reactivity, we are referring to those that are charged, the electrons in its form. But then when they become 0, that is where the electrons are going to be engaging themselves to form the full metallic form. So when we say alloy, an alloy of, say, aluminum and then iron. It is not their charged form which is reacting. It is just the zero forms which is reacting. Are you okay?
Yes, please.
Okay, please give me just 1 minute. I'll be back a minute. Yes, so is that okay? Can I proceed?
Yes, sir.
Okay, so that is the reaction with us. Of course, we can. Where is this? And I'm minimizing. Yeah, so we can also talk about the reaction of group 1 metals with the non-metals and some organic compounds. So with the non-metals, that is the non-metals, as I've mentioned some of them, like oxygen, like the halogens, but then we can also get to have non-metals like carbon, like nitrogen, sulfur, and those kind of stuff. So we can also look at their general forms. Say, for example, we take reactions. So I've already looked at the reaction with oxygen. So we can talk of reaction with, say, sulfur. And when we react with sulfur, we form metal sulfide. Are we okay? Or I should write it. When we react with nitrogen, we form nitrite. So the metal nitride, the metal sulfide. I should write it to see what I'm referring to.
Yes, Doc.
Okay, so let me clean this one. Okay, new, don't save. So when, say, for example, nitride, then we know nitrogen has the -3. So if I'm reacting it with the metal plus, it means that we just exchange the charges. So it becomes metal 3 and then N. So this is the metal nitride. And we can form with sulfur as well. So when we have metallic sulfur reacting with that, we just form the metal sulfide. And we know sulfur belongs to the oxygen group, so that's -2. So that will only form the metal sulfide. Is that okay? Okay. Now we have other reactions with organic compounds. We can't deal with all the organic compounds, but we can select few and then we'll look at those organic compounds such as alcohols. So other situations, the group 1 metals will only act as a catalyst, but not as a reacting agent, but as a catalyst. So, but we know that in some cases, it can form part of the organic compound. So for example, reaction with alcohols. So we know that alcohols are the alkyl group OH. I'm sure you've done a little bit organic chemistry. So alcohol reacting with a metal, and then this metal is a group 1 metal. We are just going to be producing the metal aqua oxide, what we call aqua oxide. So, for example, is the mercury aqua oxide, which is a good reducing agent. So metal aqua oxide and then hydrogen gas will be released. And this metal aqua oxide is a very good reducing agent, which helps us to reduce alkenes. So alkenes and then alkynes to alkanes. So alkenes, alkynes is being reduced to alkanes. And that's example is the mercury aqua oxide. That's Mg, sodium mercury aqua oxide. So that's a reducing agent. So sodium or potassium aqua oxide. And then what we know is that for alcohols, it's just going to react to just produce the metal aqua oxide. Aqua oxide is spelled AKO oxide. Okay, so the metal aqua oxide. Okay, so these are the general kind of.
Hello, sir.
Yes.
Hello, sir. Please, I have a question. Sir, the alcohol and then the metal, the reaction that you wrote right now, but is it that is it substitution? Is it taking off the hydrogen and then displacing it, or I don't know, so that maybe the next time you know how to?
Yes.
It's a substitution
alcohol,
reaction.
Yes. So the alcohol is having so we have to produce the so this is RO minus plus H minus, and then reacting with M plus minus. The M plus is more reactive than hydrogen, so it will just displace the hydrogen, so that will now produce the RO, now reacting with this metal. So it just displaces the hydrogen because the group 1 metal is reactive more than that of the hydrogen. So reactivity series.
Okay, sir. Thank you.
Okay. Yes, so that's a general kind of reaction. So if I start taking, now I'm going to be taking the element one by one under the group 1, but then their general reactions are going to be following what I've listed. Reactions with, let me minimize this, reactions with oxygen, reactions with water, reaction with hydrogen, halogens, acids, bases or ammonia, and then the non-metals in general. And then here we selected only alcohols. Okay, so they follow the same trend, so that I don't kind of waste my time repeating the reactions over. So I'll just, when I get to that reactions, I'll just jump those reactions because they follow the same trend. Okay, so I will take a lithium then. Now, this is quite interesting because, of course, we have lithium in our soil now, Ghana. So if you look at it, it occupies almost like a 0. Very minimal. So it means that countries that have this lithium should be considered as rich countries. So, for example, Australia, which has lithium, considered to be one of the developed countries. Okay, now we'll see that it's mostly, apart from the earth crust, which is so small, we have most of them in the seawater. Of course, the concentration is also that low, but then we have them in the seawater. The main kind of ore or the main source of lithium will be the spodumene, which is lithium, aluminium, silicon oxide. That's the main ore of the, where's my cursor? Okay, so you can see here. So that's the main ore of the lithium. So what it means that this compound can also be the ore for aluminium. It can also be the ore for silicon. So please note, if the elements are represented there, it's just meaning we have the pure forms extracted from the ore form. So we get to have aluminium in this form. Then its metallic aluminium is that shiny, very soft metal that we can easily extract. I think last year, so we are in 2026 now, last year, 2025, in November 2025, November 27th, this news came up. I don't know if some of you are aware of this particular news. So apparently we have this lithium discovered in the I think in the Mankesim area and then some part of the Volta region. I'm sure you are aware.
Yes, sir.
Yes, sir.
Yeah, so the past government there was negotiating, and it's so funny while we can't be doing things on our own. Always we want foreigners to come and do that for us. So they came like just like the oil. So we discovered the oil, then they came that you don't have the system to extract that. We'll extract it, we'll give you 10%. Then we agree, we'll take the 10%, then they'll take the 90% and extract the oil and take it. It's just recently I heard that the Maaya refinery have started trying to see if we can be refining some of. Otherwise, once they extract it, they take it there, then they'll bring us the gallons of the oil at their own cost in the world market. The same applies to the lithium which we discovered. So the past government says that the royalties which they are going to give to those located in the central region, I think we are in the central region, said that they were going to be giving them 10%. Then those chiefs says that they will not agree. Then the current government says that when we come, we'll give you 15%. When they came, they are now proposing 5%. Okay, so and you can just see if we are really trying here to help our country. So this is a nice mineral. This is lithium, which we use in lithium batteries. And that's the agreement now is that, of course, it says that they reject that 5%, even the 10%, they didn't take it, not the 5%. And that we rather want to be allowing ourselves to be exploited by those people outside there. And those that are going to be helping us, that one will push them aside because somebody is not going to benefit. So that's lithium. So we have lithium in our land. Now the reactions, I think we've gone through reaction with oxygen, with water, and those stuff. So I'll skip all those reactions. But for the uses of lithium, it's quite useful. Apart from we using it for these batteries, we can also use lithium as a a drying agent. So we use that as an inorganic solvent to absorb water, to dry the water when it has water. The organic solvent when it has water in that. Now, we also know that once there is other gases like carbon dioxide, once we have lithium hydroxide, carbon dioxide can be converted into water. So I think those times when COVID kind of broke, of course, the technology was already in use, for example, in the marine or submarines and then the space vehicles. So we breathe out carbon dioxide. So in the suit or in the kind of vessel, they have this lithium hydroxide, which will convert the carbon dioxide back to, or it forms a lithium carbonate as powder, which drops, and then we'll convert the carbon dioxide into water. Then we'll break the water down into the hydrogen gas and then oxygen. Then we'll breathe the oxygen back. So I don't know if you remember during the COVID time, we're having this particular, I think some of the TV stations, we saw that spraying some of these things in air. I don't know if you can see my cursor. So they just spray the lithium hydroxide, and then the lithium hydroxide will capture the carbon. So it's assumed that if the virus is part of the carbon dioxide, it converts that and drop it down from the lithium carbonate, including the virus. So it will just be depositing it down. Okay, so that technology really has been applied for quite some time. So we see this lithium hydroxide also there. I've mentioned that we can use it also as drying agents. Okay, so for drying organic species. Now, lithium is considered to be one of the powerful reducing agents. As I mentioned, like the converting them from like alkanes to alkanes, we have that. So lithium aluminum hydride is one of is a reducing agent in use in organic synthesis. Then we can talk of the lithium chloride, the hydrides. The hydrides of this lithium chloride, bromide, which really helps us to absorb water kind of content in most air condition. Of course, we know the principle of this air condition. So basically, if you ask why the air condition is producing water at the end, so that system that is outside, which is releasing water. Where is it getting water in there? Of course, the atmosphere is made up of oxygen and hydrogen. When we come to the non-metal, we see, and we have more hydrogens there. So there is this converters that converts, pick the hydrogen gas, oxygen gas, and convert them into this deionized water, which we see there. Okay, just to reduce the humidity in the atmosphere there. So the lithium chloride, lithium bromide really is what is playing a role there. Now, in terms of biological use, of course, one of the most important use of lithium in our body is when we are using lithium, for example, lithium carbonate to mimic a compound which we have in our system, which we call serotonin. Okay, so serotonin is the compound which we produce to, suppress what we call depression. So when a person is having this depression, stress, and those things, our system synthesizes this compound which we call serotonin, and then it controls that. Now, when this compound is not being synthesized, that's where a person says that I'm depressed, I'm stressed, and those kind of stuff. So in the medical kind of field, they use the lithium carbonate to mimic that serotonin so that it controls the depression there. So the lithium basically affects the transport of this sodium in our systems, which is responsible in helping us producing this, so that at the end it controls that depression that is in that. So serotonin, if we lack serotonin, we see that we'll be having this particular kind of symptoms there. You kind of, your emotion control, emotions be affected, and you become aggressive, in social kind of ranks here and there, stress, and then stress coping. That's when you are having problems with serotonin. Now, ways of trying to increase it, and that compound is synthesized in the brain. That is the 5-hydroxy typing. It's synthesized in the brain. So sometimes we have to take. They recommend you take a supplement of that 5-hydroxy typhenol as an agent, and of course that's just more or less like a supplement for what we can desynthesize. And sometimes they recommend that you take vitamin B, or you just expose yourself to a little bit daylight sunlight. Okay, not the excessive sunlight. Between 11 before 12 thereabout, that sunlight is quite useful. But after that, when it becomes very scorchy, that's a full radiation at its play there. Okay, so that can even affect your brain. When it hits your brain, there you can usually. So if we say we need sunlight, not that extreme radiation sunlight, that's not what. Well, sometimes you need yourself a simple treat like massage. Go to massage, the brain is being deceived. It starts synthesizing that compound, which I know we don't do. You see a black man or a black woman going for massage, then it means that now that's why we see black man going for a massage. Otherwise, we don't do that. And sometimes a few meditations will also get to help we synthesize that. But I'm bringing in that because of lithium carbonate, which mimics serotonin. So it's quite interesting if how serotonin can affect our health, can affect your brain, your sleep, or if your sexual functions can also even be affected, your bones can be affected. And so if you want to see what it can really cause you a serious damage, especially, for example, in the women who see this premenstrual syndrome, that PMS, really being affected. And that is a combination of emotions, physical, psychological disturbances in the ovulation of the woman. And that's possible because the serotonium synthesis is also not quite active. So it brings that kind of problem. And that's where we introduce lithium carbonate as well. So in biological system, the only lithium compound that we know to be quite effective is the lithium carbonate. So that's lithium. I take sodium. Okay, so sodium, a common form of sodium will be the sodium hydroxide, which we call the lye, LYE. So the sodium lye there. I think those times, well, now we don't see that, but it was quite common when we're living in the era of what we call is it light, eh?
Yes, sir.
Yeah.
Yes,
Yes, sir.
Yeah, now we don't see them,
Where's our
so
guys?
maybe the Gen Zs don't really
They
have
are
no
around.
idea what
They are still around.
they are still around in this era. Hey,
Yes, sir.
Hey, are you sure?
Yes.
Are you sure, sir?
maybe in a different country, but Ghana we've been able to
Say in Ghana.
in Ghana.
Ghana.
Oh my God, I doubt.
Oh, okay, no problem. It's true. They are still around.
Lights. So in that era,
Yes.
we were missing this sodium hydroxide with say is it shea butter? Okay, then you apply it on the hair so that it kills that. I think that's what's gradually killed all those. So sodium hydroxide, another common name for sodium hydroxide is Li. Okay, so that's the Li. But so we see sodium metal to be so again, if I'm talking about biological systems and match reactivities, then I'm referring to the ionic forms, not the metallic forms. Please note that. So for example, if I tell you the body needs sodium or the body uses sodium, I'm not talking about the metallic sodium. I'm talking about the sodium plus. Okay, so the metallic sodium is soft, shiny, and then it's also quite reactive in the periodic table. But we know that sodium is one of the old metals, so it derived its name or this symbol Na from its old name, which we call the nantron. So the atomic formula for atomic symbol for sodium, we see Na. But sodium is spelled Sodium. And so what it means is that it's derived from the old kind of name. Well, in the olden times, we have sodium lamps, which was trying to help us. We have these sodium lamp engines, which are available. But then what we know sodium commonly is the common salt now, not the common salt which we have. And so we have other compounds of sodium. And of course, the size of sodium is quite closer to the size of potassium. So normally where we see sodium, you will see potassium. They quite move together. Okay, so I'm treating like both together. Though I'm talking about sodium, but then I'm looking at both of them because they usually move together. So we have common compounds or the oils of sodium, like the rock salt, what we call sodium chloride, or the hetite. And we have the chili saltpeter. I'm sure you know saltpeter. But what's the
Yes.
local name for saltpeter?
Account.
Cal, yes. So cal basically is just a sodium nitrate. That's a saltpeter. So we have the chili one, which is the sodium, and then the normal saltpeter, which is the potassium nitrate. But then they are all kind of saltpeter, and it's just a rock. So a sodium is just a rock which looks like a clay rock kind of form, and that is extracted from the clay form. I think in Nigeria they mine most of them from Nigeria. The ones that are sold here, they bring it from Nigeria. And that we should also note that of course sodium the nitrate can be a mineral to to plants, but not really a mineral to humans. So sometimes you can be getting a food poisoning from this saltpeter. So I think they use it in cooking beans. The idea is that it makes it soft. They use it to cook okra so that it will be kind of slippery. Is that correct?
Yes,
But
sir.
I can tell you that the body doesn't need nitrates. So it becomes something that the body will have to fight it if it's fighting those. And they put a lot of them also in the cubes. For example, the Maggi cubes, also so and so cubes as preservatives. That's something that we ought to also take control. I think in the olden days, were not used to, or our grandfathers or mothers were not used to these additives and food additives and those stuff. And so they were living long. Now in our time, we want the food to be sweet, so we add more kind of additives. And so we life expectancy is now decreasing. I was even reading an article where it was making the argument why in the olden days it was hardly to find an obese person, obesity, but now it is quite common. Now our grandfathers, grandmothers were of a shape. Now you, after 40, you see your tummy bloating like mine. If you are here to see me, you see my big stomach, all because of additives, which we just add. And one example of them is the sodium nitrate, the saltpeter. Then we have the sulfites, the sodium chloride. So again, the reason for these common names or the all forms is to know the name and then its chemical formula. Okay. So when I mention say abite, basically I'm talking about sodium, aluminum, silicon oxide. So please, you know the all forms and then the chemical symbol. So if you hear somebody saying, I'm going to buy salt, which salt? Because every ionic form is a salt. By which salt it tells you, oh, the rock one, then it means that you are talking about sodium chloride. So and that is just that. Now we can extract this sodium using electrolysis. Of course, we understand that sodium has a +1, or it can release the electron and become +1. What if we feed that +1 ion with an electron? So that's what we call electrolysis. Then we can now be forming the metallic sodium. And again, basically, that's just applying the Le Chatelier principle, which we can easily predict which side will be favored based on the changes that happens in concentrations, in pressure, in temperature as well. So we apply the electrons there, and then it shifts to favor that. So we have sodium chloride being dissolved, and of course, when we dissolve, what it means is that we're going to be having the chlorides in the solutions and then the sodium in the solutions. Now, the chlorides in the solutions have these electrons which they can easily give up to be forming the chlorine gas. And then those so basically this redox reaction, and those that are going to be accepting that the reducing agent are going to be the sodium, which is going to accept the electrons and become the metallic sodium. And of course, once I form the metal, it becomes less dense, which I can easily. So in terms of the solution, you see the chlorine evolving and then the sodium depositing. So I can just get the sodium metal from that. And we use what we call the Daniel cell. So redox reaction. So pushing electrons well at a high temperature though. So around 600 degrees Celsius, so that we push the electrons in there. Now most of these compounds, we could easily kind of synthesize them, but then because of energy wise, it's quite difficult to get to them. And so, for example, say potassium permanganate. We use potassium permanganate in treating our water bodies. It's more or less like a disinfectant and those kind of cleans our water. But then potassium permanganate is basically potassium, manganese, and then oxygen put together. And if you look at the systems or the reaction, it's quite simple, but then it's energy involved. We have manganese because of the mining that we do. The rocks there, we can have manganese from there. Potassium from ash. So anything that we burn, like our cocoa hash, which has high content of potassium in there, we can get the potassium, mix them together, and let's pass a high energy electricity through them. You'll be producing potassium permanganate. So the process is quite easy, but then our system here doesn't really support usage of that. If we try it, you'll be paying more than 2,000 CDs within 2 minutes. So we wouldn't pay that amount just to go and produce, say, 1 gram of that. So we'd rather go and export it and then invest that. Yes. Okay. So again, the same principle here.
Hello, sir.
Yes, I can hear you.
Yeah, please. The cell, you said it's called what? Daniel cell.
Down cell. No, sorry. If Daniel cell is the first voltic cell, down cell, down. Can you hear me? Well, I don't know if I'm off, but I think I still can hear. So it's down now, not Daniel. Daniel cell is the first voltic cell, not Daniel. It's down cell, down because the sodium is going to be depositing down this the solution. Is that okay?
Yes, sir.
Okay. So we can also do same for the potassium, but then in potassium extraction, normally we get to extract them either from potassium chloride, from potassium sulfate, or potassium carbonate. And we get this into potassium chloride, the salvites, the potassium sulfate, that is the carmelite, potassium carbonate, that's the lentimite. When we get them from mining activities or mining operations, we can be getting this potassium from that. So the process is basically we crush them into a powder form so that we'll get it in a smooth form, and then we'll float it in a cell. So like sieving it so that we'll get to have it being very fine. And then we'll try to separate, we try to separate the potassium minerals from other kind of minerals there, like sodium and those things. So we use what we call collectors, the fronters, then the agitative tanks, so that we can easily extract that from there. This is what I'm trying to. So from the mining site, we get the potassium aspect. Yes.
Please, can you go back to the previous slide? This equation, you can see that the sodium has displaced the potassium, even though potassium is more reactive than the sodium.
Yes, and I told you where you see that it's possible, where you see potassium, you see sodium. Their sizes are quite closer. The size difference is not even up to 1 picometer. So though potassium in terms of reactions we'll say that is as you go down the group, is supposed to be reactive more than that, but then it means that sodium can also displace potassium.
Because they have almost the same size.
The same size. So what you are seeing here actually is the same. So they are still in the aqueous forms. The sodium chloride, potassium chloride is still in the aqueous form.
Okay.
Is that okay?
Yes, sir.
So let me correct this. It's not gas, please. Let me minimize this and then correct, or I'll correct it. So we are looking at the sodium as a metallic sodium. So not G, please. It's rather S. And then this is aqueous. The S rather is aqueous. What you are forming here is aqueous. Sodium chloride is not a solid. It's aqueous. So using solubility rules, sodium chloride can never be a solid. It's aqueous salt. So it means that you have water component in that.
Okay.
Now, I'm sure you know what I mean by aqueous salt and then pure solids.
Yes, sir.
So aqueous salt means we have water component in there, whilst a solid does not have any water. So, for example, if the water molecules are more, we call that salt hydrous salt, hydrated salt, and then the anhydrous kind of hydrated salt, meaning the water molecules is more then. Okay. Now, from that extraction, I'm just looking. So we'll look at it, grinding it into fine powder, mixing it with calcium. So that's a binder which is going to bind other kind of ores from that. And so we'll form what we call calcination. So calcium in there. We'll mill it again. Then we'll push in carbon dioxide and wash it with water. So water goes to dissolve the other kind of, salt that has been there in the mixture, then we'll sieve it. We will filter it and get our potassium, the salt form, like the ionic form, potassium sulfate. And that's the best that we can get to have potassium in there. Of course, it means that when we take it through electrolysis, then we can now separate the sulfate and then be producing kind of potassium a lot in that. Of course, we have these systems, not of course in Ghana, but then outside there, they have these systems. Quite interesting there. I'm yet to see if we can start citing these companies around where, or these factories where we can, because we have a lot of these ores of potassium and sodium here. We have the sea there, which we can easily be extracting them and then we just getting, and we also have to start exporting some of them. And it's quite funny, whilst we have all these resources, yet we are not as the industrial hub, but rather we are relying on others as the industrial hub, and we are happy when they rather make us a dumping site. We are happy. We are very happy when we become a dumping site. So they will do their kind of manufacturing and then come to drop it and says that bag it. Then we are happy. Now we are even going to them for a complete package, and then we'll just put our name on the package and bring it. And we'll localize it and make it look as if it was produced in Ghana. But it is not. It is not from Ghana. And the one that we produce, I don't know why things that are produced in Ghana are quite expensive. Of course, the manpower also contributes. So we don't want to be buying the one that we produce. And then it's quite easy if somebody export it and bring it. So this is how they use. So they put the mash thing here, which is going to be milling it. And then the process goes on until we get to have our potassium, metallic potassium clearly filtered out here. Now, in terms of biological use for sodium and potassium, this is quite very vast. Our system uses potassium and sodium, and as I mentioned, their metallic form, you always see them moving together. So most of the enzymes which we have, the sodium potassium ATPs, are common in our system, which helps us regulate transporting, say, oxygen and electrons, and then regulating the cellular kind of functioning. Most of the mechanisms that goes on is just basically because of sodium and potassium that we have. So if you take the cell, the plasma cell, we have potassium there. Talk of the ATP cycle or the Krebs cycle, which we have, the pumps that we have, we will see pumps which moves sodium and potassium ion in and out in opposite direction so that we can really balance our concentration gradient in that. So in effect, we'll see that potassium and then sodium really helps us to really maintain our systems in terms of energy. However, we sometimes store some of these metals and then we'll excrete some of them. Okay, so we excrete sodium, potassium through sweat. Sometimes few goes through the urine, and that's how we excrete that, and the fecal as well. But most of them are stored. What it means is that we should find a way of replacing the sodium and then the potassium which we have lost. And of course, we don't need much of them. I mean, we use them a lot, but then storing them. So if somebody is not exercising to release them, then it's quite, you are building more fat instead of, if you're afraid of losing the sodium, potassium, you are building more fat. So exercise is good. But I want to mention this just because of this. So sodium potassium chloride mixed with water when it's being excreted from our skin is what we call sweat. However, depending on if you check, and of course, the skin basically are aldehydes and ketones which have arranged themselves. So if you say skin, these are ketone, and then some aldehydes combining to arrange themselves, and so they are pores in that. So this is the pores that helps the excretion. So the skin arrangement is quite different from where we find. So if you take for example, your head, where your hair is, the skin arrangement is different from your face, and it's quite different from your hands, your legs. So your armpit and those private parts are also quite different. Now, I just want to mention that. So if you are sweating, we should note that the sweat or the kind of sodium potassium that comes out of your open skin is sweat. It's purely water and then salt. However, the ones that are coming from your armpit is not sweat. These are proteins combined with this potassium and water. Okay. Now, the system is said that when a protein goes out of the system, it has to be broken down by enzymes. Now, these enzymes, they break down the protein, and then we'll be waiting for another protein to be released so that they will break them down. Some of them, they die off and dry off and become these whitish things that you see under the armpit. Well, the enzymes that breaks down these proteins and the private parts or the armpit are quite pungent. They come with kind of a different scent altogether, and this is what creates body odor. Okay, so if you are having body odor, basically that's the origin of that. So it breaks down, and then these enzymes are there. And most of the times, these enzymes operate in a basic medium. So if it's a basic, then it means that we need to neutralize it, or at a point you want to stop it from excreting CRA. And so if you want to control body odor, well, in our local form, we'll say that use lime, which is citric acid, balance it with, say, an ash, so potassium hydroxide, and then neutralize that enzyme. It's a good way of controlling that body odor. Or you use what deodorant, of course, is more acidic form, so we'll use that to neutralize that. Or use what you call the antiperspirant. Antiperspirant means you don't want to sweat. You are blocking the pores so that there'll be no sweat coming out. Okay, so that there'll be no protein settling that point. And it's quite disturbing. When I get to this point, sodium and potassium, I usually want to stress that quite disturbing because some have a strong pungent body odor, and the sodium potassium there is finding its way in the wrong place. So that's how we control. That's just an idea of that. But essentially, we use sodium and potassium a lot in our table or common salts in the industry for food production. water treatment, soap making, food additives, and detergents as well. We just use them a lot. Well, again, the reaction will follow the general reactions which we just went through. So I'll just skip those reactions as well. Oh, just that. Okay, now we have compounds which we've mentioned, the sodium carbonate, sodium hydroxide, potassium hydroxide, and those stuff are just compounds coming, or which are compounds of the group 1 metals. Now, how do we produce them in terms of their synthesis? Well, if I have a salt mixed with ammonia, and then add a little bit acid, carbonic acid, I'm going to be producing bicarbonate. Now that bicarbonate can also go through the reverse reaction to produce sodium carbonate, and then carbon dioxide is going to be released. And that's what we see in our blood. So oxygenation, deoxygenation is just bicarbonate converting to carbonic acid breaking down to carbonate, and so it goes there just because you have introduced oxygen there, goes there to just break down, then at the end we release carbon dioxide and then water at the end. Okay, and that's the production as well. Well, other kind of method of producing this sodium carbonate, and this sodium carbonate I mentioned is used in food industries and those stuff as a preservative. So we can also use when we begin heating the sodium carbonate bicarbonate hydrates. When we heat it, we'll be producing the sodium carbonate as well. So this compound will just be producing that. Now, one of the common bases that we know is the sodium hydroxide, potassium hydroxide, which of course is quite useful in making soap. It's useful in acid-base reactions and those stuff. But we should know that we use, say, potassium hydroxide as an electrolyte in UPS. That's the uncorrupted power kind of supply. UPS is sodium hydroxide, which helps us, is used as an electrolyte. The liquid that we find in that is that sodium hydroxide solution. Now, in the olden times, before the reinforcement of lead poisoning came, then there was a combination of potassium nitrate, charcoal, which we call carbon, and then sulfur. If you combine them, that's what we call gunpowder. Now, of course, we have put in lead because lead also causes lead poisoning, so that it can easily kill so easily. But then for gunpowder, the combination is 6:1:1. That's sodium nitrate 6, 1 of, so if you are using, for example, teaspoon, take this 6 teaspoons of sodium nitrate, 1 of carbon, then 1 of sulfur. You mix together, that's what you call the gunpowder. Okay, so that's something that we're using in the old. I think now we have moved from here to be using the lead pellets. So they melt the lead and then make it in a pellet form and pack it into the bullets, so that when they fire, the lead will just move. And then when it moves and it gets into contact with an organic compound, we'll come to the poisoning lead. Then an organic lead is extremely poisonous, so it begins poisoning the system, and that's we use that. And it's quite dangerous because lead continues poisoning the system. So if, say for example, they use lead in killing, say, an antelope, then you go to also eat that antelope and the lead gets into your system, then the poisoning continues. And so we get to have that that system. Okay, so that's group 1. As we are going down from rubidium and the cesium and francium, these are quite radioactive, so we don't really have much importance or use applications of them. All we know is that they are radioactive. So we have not really engaged them, and they don't have any biological use as at now. As far as I'm concerned, I don't know any biological use for francium, cesium, and rubidium. Okay, group 2. Now, group 2 is the alkaline earth metals. Well, that means that we're talking of the Lewis bases there. So the alkaline earth metals, which is beryllium, magnesium, calcium, strontium, barium, and then rhodium. So we get to have these metals also under group 2. Okay. So again, before I take them one by one, I look at their general reactions. Is that okay? So their general reactions for group 2, reaction with water, just as I did for the group 1 metals, group reactions with, and that's what is much as a chemist, that's what we are looking at, the reactions, the synthesis, the compound. That's what chemistry is all about. So if you really want to enjoy chemistry, then that baseline really stands. I think I show you that baseline. So if you look at it, we have different forms of 4 major branches of chemistry. 4 major branches. The others falls under any of them. So we have inorganic, organic, we have the physical, and then the analytical. These are the 4 major. The others will either be coming from organic or be coming from inorganic or physical. Now, with the exception of physical, that uses physical laws. Okay, so physical chemistry uses physical laws. So you see that for that, you'll be doing much of calculations there. Inorganic, then organic, deals with just chemical reactions. Of course, how we analyze them is where analytical chemistry comes in. Now, organic and inorganic, basically we are looking at what is the compound. What's the name of the compound? What does it look like? So the structure of that compound, how do we synthesize that compound? What does this compound entails, or that is how it engages its environment. So that's all about chemistry. And that's a baseline. So those of you are running for chemistry, it's very simple. Chemistry is the cheapest course you can find, because that's all. If you look at the entirety of chemistry, now as you're advancing, the basic core still stand. Organic, inorganic. Well, what is the compound? I mean, what is the name? How does it look like? That's the structure. And then how do we synthesize it? How does it engage its environment? That's reaction. And where do we get it from? Where is the source? The ore. And that's all about chemistry. And that's all we are doing in chemistry. In the advanced level, that's all. So as I said, we're exception of the physical chemistry where you do some calculation. The other, you are just, so analytical puts a little bit of the physical and then bring the inorganic, organic together and do analysis with them. And this is analyzing chemicals. So please, that's chemistry. So the group 2 metals. So we look at their reactions and we consider reactions with water. And here the focus here is to be able to predict the product. I mentioned the ore. The focus of you knowing the ore is just to know the name and then the chemical formula for the ore. Okay, now the reactions is just to be able to predict that when I react with this one, this is the product that I'm going to be getting. Would that be difficult? Please, would that be difficult? Okay, let's try something. Okay, so where's my board? Okay, so let me clean this one. Oops. Okay. Yes. So we're reaction with oxygen. This is group 2. So I'll just make it M2+. Okay, so M2 plus, and that is going to be reacting with oxygen. Well, in the first case, in the group 1 metals, we saw that we had 3 different forms of oxygen in the oxidation form. We have the oxide, the peroxides, and then the superoxide. Please, do you remember?
Yes, sir.
Okay. Now in this form, we are only going to be having only 2 of this oxygen reacting with them, not all the 3. So it's only the oxide and then the peroxide that can react with the group 2 metals. In the group 3, in the group 1, all the 3 oxides can react. Oxides, peroxide, superoxide. But in group 1, it's only oxides and then peroxide that can react. The superoxide cannot react in this case. So for example, I have M2 plus and then water. With oxygen. What it means is that I can form the metal oxide, okay, or the metal peroxide, the metal oxide, and this is what that's the oxygen we can. And the various that please. Are you asking a question, Joseph? Okay. So, for example, magnesium is 2 plus, and then it reacts with oxygen to produce magnesium oxide. Okay, and this magnesium, of course, it's really bent. I want to take them one by one. Magnesium really bent. Very because this very bright light when it's burning. So when we are doing, I think there was one experiment we did here with the regular students. I don't know about people that we use magnesium, and that has to do with the exothermic and the thermic reactions. And then magnesium, when we get to that point, we ask you that you don't look at that burning flame because your eye can be affected. Okay. Now we can also see the other metals which can form the oxides and then the peroxide. So please, Joseph, is it an so can you use your mic? If you are not asking a question, just mute the mic. It's not available. I can't mute it also from here. It's distracting. Okay. So, say for example, we can have another example, barium. So barium 2 plus the oxide, we can form the barium oxide. We can also form the barium peroxide. Yes, Yakubu, Yusuf, mute your mic.
Joseph is giving us some feedback.
Sorry, I didn't get you.
I said Joseph is giving us some feedback, so if we can use
I don't know. I can't mute because I'm not the one in the call. And I don't know if he can hear us. If you can hear us, I'm asking Joseph. It's not my name. Joseph, thank you. I don't know if I should call you a boy or a man. Thank you for disturbing the class. Okay. So let's move on though. Okay, so that's reaction with oxygen. Now let's see reaction with water. So can somebody help us to predict what it will be when we are reacting M2 plus water? What do you think should be? In the first case, it was hydroxide. Now in the second 2 plus, what do you think it should be? Yes, who can help us?
Oxide. Metal hydroxide.
No, in this case, we only produce a metal oxide. And
Oxide.
then, yes, and then hydrogen gas will be evolved. Okay. Now, let me state that in that group, beryllium will have no reaction with water. Beryllium cannot react with water. But then starting
Hello,
from
sir.
magnesium, yes.
Please, can you explain why because I asked the same question in group 1, but you said that one, it only forms oxide with oxygen. Now, in
Yes.
this case, hydrogen is reacting with a group 2 metal, but it is also producing oxide and hydrogen gas.
Please,
Why?
it's not hydrogen, it's water, not hydrogen.
Sorry. Yes, so it's reacting with water and it is producing metal oxide and hydrogen gas. That's what I'm trying to say.
Yes, and that's so in the group 1 metals, note that in group 1 metals, when they react with water, then we are going to be producing hydroxide and hydrogen gas. But in group 2, we don't produce hydroxide, but we produce oxide and hydrogen gas. And you want to ask why? Why? Because in a simple kind of the water exists in this form. I'm sure you agree with me.
So, sir,
Is that
like
correct?
calcium, yes, sir. Yes, it's correct, but I want to follow up. Like calcium hydroxide, calcium gets hydroxide, right?
Yeah. So I'm building point two. So I'm giving you one reaction. I'll come to that hydroxide, and I'm giving you exceptions that beryllium have no reaction when it comes to water. Magnesium will react with water. So I'm coming down the group and I'm going to tell you how they are going to. All of them has their own unique way of reacting. Unlike the group 1, it is just one way. But then in group 2, all of them are going to be having a unique way of reacting with water. So can I proceed?
Yes, sir.
Okay, so again, note that. So if we take the group 1 metals, let me minimize this. If we take the group 1 metals, we have beryllium, we have magnesium, we have calcium, strontium, barium, meaning we are getting to radioactive and those stuff. Now again, when we are reacting it with water, beryllium will not react with water. Magnesium will react with water, but it will form an oxide and then hydrogen gas. Now going down, calcium, strontium, barium will react with water and produce hydroxide. So note the exception. Okay, so the most stable form will be the hydroxide from calcium. So the oxides will be produced from calcium going down will form the hydroxide, which is more soluble and more stable as well. So if I should break what I'm saying again here, so I said for beryllium, there will be no reaction. Let me clean this up. So for beryllium reacting with water, there will be no reaction. Now for magnesium reacting with water, it doesn't form hydroxide, it forms just an oxide. It can't form the hydroxide. But then calcium, strontium, barium, when react with water, the most stable form will also be a hydroxide. Are you okay now?
Sir, please, but I want to find out. So, what substance or compound does magnesium react with to form magnesium hydroxide?
A base, a strong base. I'm here to come to the reaction with bases.
Oh, okay, sir. Thank you, sir.
Yes, but in terms of reaction with water, it will not form the hydroxide.
Hello, sir.
Yes.
what caused
Yes,
the differences in these reactions?
we are going down. Reactivities of them is going to be changing. So how they engage those compounds are going to be changing. So for example, how they engage, say, oxygen. You know, when they engage oxygen, ideally, for example, the oxygen should be having the oxide, the peroxide, the superoxide. But you see, as you are going down, we can't be forming the superoxide. So we can only have, so as you are going down, their reactivities are going to be changing. So that is going to be causing the differences in how they react with a particular kind of compound.
Okay. So and it means that this compound they form is the stable form.
The stable, not that they can't form, but then the stable form.
Okay.
So not that with water we can't have the oxide, but then the stable form will be the hydroxide of calcium, sodium, and then barium. The hydroxide becomes a stable one, and of course that's more soluble as well. So
okay.
Calcium hydroxide is more soluble than calcium oxide.
Okay.
Okay, so that's that. Now we can also have a reaction with acids. Okay, we can have a reaction with acid, and of course, we can use the common acid like the HCl. So Mg2 plus HCl, moving to form. Can you predict for me?
Yeah, it will be
metal chloride.
So
metal chloride plus hydrogen gas.
Cl2 plus H2.
Yeah.
Is that okay?
Yes, sir.
Yes.
Okay. So I mean, we can also do same for other kind of acids. Say, for example, sulfuric acid. When it reacts, definitely we're going to have the sulfate of that metal plus the hydrogen also coming out.
Yeah.
Now, what about reaction with hydrogen gas? What are we forming?
It will form the metal hydride.
So the Mg2H2. Yes, so that's the metal hydride. It's different from the MgH. Okay, so note that. Okay, so that's a metal hydride. Again, this metal, the group 2 metals, the hydrides of them are also vigorous, violent when it comes to reacting with water. Okay, so again, we should also note when we are dealing with these metal hydrides. Then we can also look at the reaction with, say, the halogens. I'm sure that is quite simple. Where we should be producing the metal hydrides, the metal halides rather. So
it's metal halides.
Yes. So calcium chloride,
So, say,
those kind of yes.
Please,
Yes.
so I want to find out that is there any factor that you can use to determine whether a group 2 element will react with, for example, the water or other substances that, for example, you said beryllium like this, it will not react with water. Like, is there any factor that you can use to determine that this particular...
Yeah, so they can all react, but then with exception. Okay, so in that group, what we should also note is that though we say that they behave the same, but then they can have some few exceptions. Okay. Later we'll go in, when we take that one by one, we'll just to note that beryllium behave exactly like aluminium. Okay, so compounds of beryllium are the same compounds which aluminium forms. So for example, in terms of corrosion, you don't see beryllium corroding, you don't see aluminium corroding. But then the other metals that follows beryllium, they are going to be corroding. You get it?
Yes, sir.
Okay, so say
Yes.
normally at the let me use the lower level explanations. Normally, if you read the book, they say that elements in the same group, they have the same chemical properties. But looking at what you are explaining to us right now, it means elements in the same group too are reacting differently with the same compound, like water. So it means their chemical properties
Okay.
are a bit not the same.
Okay. Let me again explain what we mean by chemical properties. Now, if I say a chemical property, what that means it means is that they have the same kind of behavior in terms of electrons. Okay, so they have the same chemical properties in the sense that they have the same number of electrons at their valencies. But then chemical properties does not mean reactions. It does not directly mean reactions.
Oh, okay.
How they are going to be behaving because of the electrons that are there. That is what we are calling chemical reactions. So when you put them in an environment, how are they going to be behaving? Well, they will behave the same in terms of the electrons that they are having. But then when they engage the environment, they are going to engage in the environment differently. That is why you can have an element in the same group which is radioactive, but then another element in the same group, it is not radioactive. Meaning when it engages its environment, though they have the same chemical properties, but then their environment is quite different. The energies which they possess will be different. Again, when you are going down the group, that will even tell you that though they have the same chemical properties, but they have different levels of energies. The electrons are in different energy levels. So they can engage the environment the same way. Are we making sense?
Yes, sir.
Okay. So that's what have we gotten? So hydrogens and then the halogens. How about the nitrogen? Nitrogen.
You form metallic nitride.
Nitride. So again, say M, please we can balance that equation. So nitride is 3 minus. So what
Yes,
it means is that I need 3 here, I need 2 here to form the Mg. So for example, magnesium. So that is going to give you 3 for this, 2 for that.
Yes.
And the balance equation. And but then at the end, we'll form of course, the metallic hydride. The example is magnesium nitride. And most of the times, you again see that if you engage this group 2, it's only magnesium that really will react. But theoretically, they can also do that. But if you put them in the experiment and you expose nitrogen gas, so this is nitrogen gas. If you put nitrogen gas to magnesium or all the other metals, magnesium will react faster to form the nitride than the other kind of metals. Okay, that's something. Then we can look at the reaction with carbon or carbon dioxide, and then we can look at the reaction with acids and then bases as well. So let me clean this. Let me look at the reaction with carbon. The non-metals, reaction with non-metals. So Mg2 plus reacting with carbon. What do you think the product should be? Yes. And you cite one common example of that product. What's the product? Oh, I thought metal carbide. For example, calcium carbide. I'm sure you've seen that compound. White is compound, very common, and it's being used by this auto kind of those that do the weldings and those stuff, because calcium carbide reacts with water to produce ethylene. That is a gas, ethylene gas, and then of course there will be this the calcium in the system. Now this calcium oxide also. Now this ethylene gas with a little flame will explode. So that's a bombardier or something that they do. If you come to campus, the Casford people, so they buy calcium carbide, add a little bit water, you see it bubbling up. Then with a light, you hear that boom sound. And then in the autos welding side, so it's either use the soda welding or use this calcium carbide welding. I'm sure you are aware. And the calcium carbide with water produces acetylene.
So the calcium carbide, it is a metal, right?
The calcium carbide, what do you mean by it's a metal? It's a whitish powder, it's solid.
No, there is one that is solid. It is like a stone type that they put in the water.
It's not a stone. That's a solid. It's not a metal. That's calcium carbide. It's kind of soluble in water. It breaks down, but then it reacts vigorously with that water. It's not metal. Now, when we say metal, that means that this is purely like calcium metal. But once it reacts with other non-metal, it becomes just a solid. It's not a metal again.
Sir, like my brother is saying, it is solid, like stone.
Yes, and that is calcium carbide.
But it is not in a powdery form when it is in it.
No, it's not in a powder. But when after that, you'll be getting your byproduct, the powder form, which is the
right. That is where it becomes in the powdered form.
Yeah, so that's hard solid that you are talking about. Is a calcium carbide.
That is it. But it is not the metal. So, that one we understand.
So sometimes they break it down into like stony type, depending on how much you want to buy. You can get a big stone, small stones, and those stuff. That is calcium carbide, and that is metal reacting with carbon to produce. So if I balance the equation, that is going to give 2 here, so that it becomes a metal carbide. And note that the metal, for example, calcium carbide reacting with water produces acetylene gas, and then that will be kind of highly flammable. Yes.
Yes, sir. With the formula of the calcium carbide, the subscript 2, won't it be at the calcium rather, since the carbon will have plus or minus 4 and calcium will have plus 2?
No. So we are looking at carbon now becoming just 1. Now don't carbon has oxidation forms depending on the compound that it forms. Now, if you are looking at it like which of them is a stable carbon, is when carbon forms a covalent bond. And that is where we have the plus or minus 4 in covalent systems. So when a carbon forms a covalent bond, then the oxidation state of that carbon is plus or minus depending on the position you find yourself. Now, when carbon becomes a non-metal and reacting with that, then it will have the effect of that metal that is attaching itself. So this time, the calcium carbide is an ionic compound.
Yes.
Okay.
Yes.
Okay. Now, can we proceed?
Please, I didn't get a reason why it is two subscripts. I didn't get a reason why.
2 because the metal is plus 2. So carbon is plus is minus 1 here. The metal is plus 2. So we just change, and then so there's 1 here, but we don't normally write it. So the metal now is behaving like a non-metal, which is like the halogen, a non-metal.
Okay.
It's not a covalent system. This compound, the Mg2 is an ionic compound. It's not a covalent compound. So, for example, a covalent compound like carbon dioxide, okay, then you can say that the oxidation form here is +4. Okay, because the oxygen here is -2, so times 2, that is 4. So carbon here is +4. That's covalent system. So in covalent systems, we can have the +4 -4. Okay, that's why it doesn't want to give. So we say carbon is tetravalent. It can't give all H4, and then it can also take all 4 from 1. So it has to share. So it's tetravalent.
So in short, can I say that when it forms ionic compound, it has a charge of -1?
It depends on the ion which you are dealing with. So if we have, say, aluminum carbide, the carbon will be having 3. Okay, so it takes the charge of the ion that the cation that you are dealing with. So if it is sodium, then we'll just have sodium carbide, NaC.
Okay.
Okay, so it takes the charge of the metal which is attaching itself. So in that case, we'll say that then the carbon is -1, behaving like the halogens.
Yes, sir.
Okay. Yes. Now, +2 metals reacting with ammonia also produces amide. I think, sorry, on the timetable, are we supposed to go for a break or I should continue?
We can break for a while.
Yo, Marty. So let's break for just 10 minutes. Or how much time do we have in the break?
Yeah, 10 minutes is okay.
10 minutes.
10 minutes. It doesn't mean go off for 10 minutes. Just mute yourself, find some water to drink, and then 10 minutes we'll come back. Okay, so 10 minutes.
Yeah.
Eliasu.
Tomorrow first Sunday. Yes. Everybody should wear a dress. No. It's communion. Wear your Christmas dress, New Year dress. Huh? Mm. 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 Oh, I see.
Yo, bushafo yɛ kɔ break ana? Yo, bushafo yɛ kɔ break ana?
Yeah, we're on break.
Oh, okay, thank you. Ato apome.
Yeah. I'm not the Musa.
Na me na do. Ate bebe ade no ko ta dindin mo.
As it.
Eta dindin mo papo.
Charlie.
Obe vim.
Yamike.
Ba o mi so obafa.
No, but
Okay, no yawa.
yeah. Mm. Okay. You came to rest. Mm. Okay. Enjoy your day.
Hello, so I guess it's 10 minutes. Exactly 10 minutes, so we can continue. Hello, can you hear me?
Yes, sir, you can continue.
Okay, so that's 10 minutes. Okay, so the reaction with so I did carbon, and so we can look at carbon dioxide. So reaction with carbon dioxide, again, we'll just produce the oxides and then the carbon. So magnesium reacting burning in carbon dioxide will produce so magnesium reacting with carbon dioxide will produce magnesium oxide and then carbon. Let me clean this and it looks clumsy there. Okay, so we'll produce the first one. So we'll produce the oxide, and then the carbon or the charcoal, which is going to be released at the end of it. Then reaction with ammonia will also form the amide. So the metal 2 plus ammonia will form the metal amide. Will form metal amide, what we are calling the nitride, then metal amide, and then the hydrogen gas. If we want to balance that, that is 3 moles, 2 moles here. Then the metal amide, and then the nitrogen gas also. Okay, so that is the general kind of reactions that we can just see. Now let's take them one by one then. So beryllium. So beryllium is just the first element in that periodic table. I mean the group 2 group, and that is it behaves quite different from the other metals that we have. Of course, it can just go through this what we call cosmic, produces cosmic that radiation that we can engage it in some nuclear reactions to be producing some of these electrons that we are going to be getting. If you look at it, the group 2 in general will just be having 2 ionization energies, the first and second ionization energy, and beryllium is going to be having the highest of them all, highest ionization energy. Now, beryllium's compounds which exist are the hydrides of beryllium, the halides of beryllium as well. So the beryllium fluoride, chlorides, then the beryllium hydrides. But the most common ore is the berry, this greenish rock that we see. So berry, which is the beryllium aluminum silicon oxide, which is berry. That is the common ore for aluminum. But we have other compounds like the oxides, the halides, the hydrides of this beryllium that we have. So the ore, that's the berry, can be converted to the beryllium oxide. Then this beryllium oxide, when we heat it, can then release there's the beryllium metal that we have. So we should just know that. Now we'll see that beryllium can be used as an alloy hardening. For example, copper alloys, we just add beryllium to it and then it hardens that. As I mentioned earlier, they can engage in these nuclear forms. And so we use beryllium as a Oh, so sorry, David. Okay. So beryllium is used as the windows in the X-ray tubes, as I'm showing here. Oh, sorry. I thought I'm so sorry. Sorry, I'm still talking, but then I'm showing you the yes. Sorry. Okay, then let me go back and then yes, the beryllium ore. Yeah. So that's a berry. So I thought I was showing, not knowing I was showing the white gold. Okay, so this is the berry, the greenish rock. That's what we call it. Okay. So beryllium is used in these X-ray kind of forms. Well, beryllium can be used in these nuclear reactions I mentioned earlier because it can be releasing neutrons as some kind of through radioactivity can reduce neutrons. So we use beryllium as neutron moderator. It moderates neutron in these nuclear reactors. Most of these nuclear reactors, it produces neutron very fast. So it's used as neutron reactors in these nuclear reactors. For example, it's quite effective when it comes to fission chain reactions in radioactivity kind of processes. Well, in terms of biological use, we clearly don't have any biological use for beryllium. Now, magnesium, very popular and very useful to us as well. So one of the minerals which in terms of biological is very important to us because our system is made up of enzymes, a lot of enzymes, thousands of these enzymes, and 300 of them are in our body are beryllium, magnesium related. That's a magnesium complex enzymes. So it functions well in our muscles. So you talk of our skeleton, the bones, you can find magnesium there. Regulating blood sugars, you get to see magnesium also there. So in the nutshell, it really helps us to balance our immune system. That's magnesium. So if we lack that, we try to get the supplement of this magnesium as well. So we get magnesium from foods like nuts, banana. We can also get it from the avocado pear, those vegetables that we can talk about. Ideally, an accurate intake for every human being is calculated that the minimum for children should be 30 milligram, but for adults who are, more than 30 years, you should be looking at having more than 400 for male and then 300 for female. Okay, and clearly magnesium really helps us in energy production. So that's why males need to be consuming much because we burn much energy than the female burns. Much, except the female is into kind of sports, but men burn much energy than the female burns energy. So food that I'm not by that saying that females are weaker or something. Some females are very strong, and in fact, emotionally, females are stronger than men. But then our societies try to put it the other way. Men are weak in our society. That's why we project men, but females are quite strong because ideally the work that a woman can do, I can't do it. They'll be the last sleeping, they'll be the first waking up, they'll work throughout. If I try that, I'll break down. So I don't by saying that they are there, but then by consumption we'll see that. Then we'll get a lot of them from our locally produced chocolate, our cocoa. We get a lot of magnesium from cocoa. And I think at a point the government wanted us to really look at it. And so if we talk of magnesium and magnesium deficiencies, you see that it really will cause some symptoms like fatigue, you can't sleep, you have migraine. I'm sure you understand or you know the difference headache that we have. Some people immediately they feel pain in the head, then it is paracetamol. Please note that headache can cause when we have high kind of acidity in our stomach. You can have headache. When you don't sleep well, you can have headache. When you are stressed, you can also have headache. So it's not every time that you go and take medicine. Paracetamol is a base. So it just goes there to neutralize the system. But sometimes some of them you need extra sleep. Sometimes you need to dilute the system by drinking more water. But then when we lack magnesium, you see that your sugar level becomes not stable, have muscle cramps, excess stress, and those kind of stuff. So, and we get more from the chocolate that we are ignoring. And it's so funny that we produce chocolate, we produce cocoa, but then our chocolate is the less expensive chocolate in the whole world. Switzerland doesn't grow chocolate, but Switzerland chocolate is the most expensive in the world. You can check. And they come to buy it from Ghana. They buy their cocoa from Ghana. And then Swiss chocolate is the most expensive in the world. The Ghana chocolate, the King's Bite, is the cheapest you can find in the world. But yet we don't even like it. Unless you travel, then you miss our Chocomilo and then those chocolate that we have. Okay, let's move on to other compounds that we have. So, for example, magnesium, we can have compounds of this magnesium like the magnesium hydroxide, which is an inorganic compound. We call it the milk of magnesia, which we use in stomach acid. I don't know if you have seen that before. In other words, they call that transilicate. I don't know if you are common to that. And that's a brosite, magnesium hydroxide. Okay. And that's milk of magnesia. Then we have the dolomite, which is calcium carbonate, magnesium carbonate. Okay, so for that milk of magnesia, in terms of we use that as more or less like laxative for constipation control. Okay, so or when your stomach is paining, the antacid, when you have more acid in that, it helps to dilute it because it's basic in nature. Yes, then we have the epimite, that's a magnesium sulfate, the hydrated one. It's also some compounds that we have as a magnesium compounds. Well, again, the reactions, I've written them, but then I've already taken care of them. Now, in terms of uses, we'll see magnesium being used a lot. For example, biological system, as I've mentioned, is quite easy. In terms of aside biological system, we have them as being forming because of its weight. We add it to some light metals to just reinforce those metals. In terms of batteries, that's what helps us to have this cathodic productions as well. And that's magnesium creates, that's a blood of a plant. So in humans, we are, of course, that's what makes us living things. So all living things has what you call a porphyrin ligand. That porphyrin ligand, maybe I should draw that. The difference between us and plant is the ion, that ion differences. So if I have that porphyrin ligand is basically N, and then N, and then we have the bonding stuff. Sorry, this is to this one, and we have this, and we try to balance it with the double bonds. Okay, so this porphyrin ligand. Now the metal here is what makes the difference. So in our case, we have ion, which changes from ion 2 plus, and when it's oxidized, it goes to ion 3 plus. But this system is what you are calling the hemoglobin. Hemoglobin, that's what we call blood. So in other words, when we say that you are lacking blood, what it means is that the iron content in the porphyrin ligand is limited. Now in plants, the porphyrin ligand has magnesium in that. So the chlorophyll, which you see, is magnesium in porphyrin ligand. That's what we call chlorophyll, the green pigment of that plant, which helps us in going through photosynthesis, preparing. So in this case, what happens is that there's a reverse of process. The hemoglobin is using sugar to produce oxygen, but then the chlorophyll breaks down sugar to produce, it breaks down, we breaks down the sugar to produce carbon dioxide and water, and then the chlorophyll rather use carbon dioxide and water to produce sugar. So that's a difference. So the green pigment, so the essential element in plants will be the magnesium 2+, whilst we will be the Fe2+. That's the difference between so that's the green pigment that we see. So that's greenish. Well, ideally, iron 2 is also green, but then it changes from iron 2 to iron 3, which is the red. It's oxidized. Then it becomes red, then green, red, green, red in that kind of form. But so once you expose it to oxygen, it changes to become reddish. So that's why ours is, so the iron 2 3+ is a reddish color that we see, the pigment in that blood. And then that is a difference. So magnesium is quite vital to us as well. Well, we kind of use magnesium in treating some kind of diseases and some chronic diseases as well. So type 2 diabetes, for example, it's magnesium that we use in treating that type 2 diabetes. And migraine, we should have magnesium in the bone healthy or bone health. So bone basically is a mixture of.
Please, you are not seeing from.
Hey, sorry. Thank you. Yeah, so bone is basically a combination of calcium and magnesium. So it means that once you have bone issues, we sometimes use bone magnesium in trying to improve the bone health. And of course, it helps to regulate, magnesium helps to regulate the calcium and then the vitamin D levels in our system. So that says that. Now, the compounds like the, it's rather, so please, I'll correct this and send it. Magnesium hydroxide, not very long. I'll finish talking about very long. I'll take this out. But then it has many functions, as I mentioned, bone health, diabetes, in treating diabetes, we use magnesium. In cardio kind of health, we also have magnesium there. For example, this arthritis, we use magnesium in treating that. So it means that the magnesium deficiency can really cause our health. Well, we don't have any kind of backside of magnesium. In excess, the body stores this magnesium and later reuse them. So it stores them in the bone marrow, like the calcium. It stores them in the bone marrow and then reuse this magnesium as well. Again, I'm not talking about metallic magnesium. The ionic magnesium is what I'm referring to. Okay, now calcium. Well, we cited one example of this calcium, but then this is the whitest metal, a little bit clearish whitest metal, which we find in most of our. Yes.
So please, before you go to the calcium, magnesium, when you are in hard water.
Yeah.
I want you to help me with this hard water, the magnesium ion. Is one of the cations in hard water that causes is it rusting, or how does it occur? Please, if you can.
So it's not only magnesium, we have calcium. So that's where we have to measure the concentrations of the ions in the water. So when we have a higher concentration of calcium and magnesium, then we are saying that it will not lather easily. and that is what we call hard water. The soft water means the concentration is quite low. And we get it from, because once the water engages the soil or soil, it goes through and pick these minerals from, and these are soluble in water. Calcium and magnesium are soluble in water. So once it's picking more, the concentration increases. And again, it can easily also engage oxygen to form, if you remember, so we can form the oxide and then the hydroxides of them. So that's what causes the corrosion. And then it's why we say rust. It's only iron that rusts. Iron, Fe. The other metals don't corrode.
Yes.
Okay. So the concentrations of these metals there is what creates that. But then they are essential metals. Calcium and magnesium in hard water are essential metals for our body. Yes.
So my next question is in SHS, one of the questions they normally ask is about whether the iron, especially magnesium and those ions, whether they are soluble in maybe like ammonia and those things. Is there any factor that you can use to determine whether you add in excess and then in drops to know whether it will dissolve or it will form a precipitate?
You mean the metallic forms or the ionic forms?
For example, like we are talking about magnesium. So magnesium will react with ammonia. So they can ask a question that when maybe ammonia reacts with magnesium, maybe in drops, does it form a soluble substance or a precipitate or and those things? That's what I'm asking.
So you are taking us back to the reactions with ammonia. Is that what you are saying?
Yes. So that yes.
Yeah. So the nitrites. So again, when we follow the solubility rules. Okay. So when you follow the solubility rule, the nitrites are insoluble, with the exception of the group 1, and then lead and some lead, mercury, and then silver. Then they become soluble. So if you have group 2 metals, I think I just have to confirm. If you have group 2 metals, then we are going to be forming that amides, which are insoluble, solid.
Okay.
So, and the group 2 is calcium, where beryllium is out. So magnesium, calcium, strontium, and barium. Again, the last one is also out. So we can form soluble in ammonia, but then they are insoluble in water.
Okay.
So sorry, they are rather soluble. They dissolve in water, but then they don't dissolve in that base. The insoluble means you can't dissolve. The soluble means you have dissolved. Yes, so they are soluble in water, but then in bases like ammonia, they become insoluble. Okay, so that is so in water, the one that was asking about the hard water, that's where we get that. But the point is that these metals are essential to us, except when we have other metals present, those that have high densities and high molecular weight. That is what we call the heavy metals. So the heavy metals are those metals that have high molecular weight and high densities. These are not really, not all of them are essential to us. Some of them are essential, like iron is essential, it's an heavy metal, but then it is essential. But then most of them are non-essential, so they would rather poison the system. But then magnesium, though the concentration is high, does not cause any problem to our system. Of course, if we get it in excess, the system reacts, but then it will balance it so easily. Is that okay?
Yes, sir.
So if we talk of hard water, then that is what we should rather be looking at in terms of drinking than hard water. If we can take care of the other heavy metals in that, then the hard water becomes the most safe to drink. And that, I'm sure you understand where we had the name mineral water from. So in the olden times, so in the olden times, they were selling it in the pharmacy where you have water which they have intentionally dissolved calcium and magnesium in that. That's where, so they bottle it like Coke. They bottle it like Coke, and they were selling in pharmacy. So if you are going to buy, then they'll tell you, if you go to the pharmacy, buy mineral water, the one that has calcium and magnesium, not the ordinary water which they were using cap to be fetching for us to drink. Those of you are a little bit older than me, you came to meet that. Okay, so it was this mineral water that they started adding flavors. So that's where Coke and Fanta came from. So then they added Coke, these flavors and colors to that. And so we're then calling them minerals. So Coke, Fanta, that's where we're calling them minerals. So minerals, Mikoto minerals. That's Coke and adding Coke flavor, Fanta flavor, or color to that. That's minerals. Then later, then we decide, okay, once I measure and then I see the content of magnesium and calcium high, then I call it mineral water. That's where they started bagging it, sachet water. The sachet water, which we were calling mineral water. So that's where the sachet water also came in, that mineral water. But I don't know how they ended up calling it pure water, because that is not pure water. But I think in relatively, they were comparing it to the one that they were selling in the coolers and the buckets in the town with the caps. So thinking that this one is well packaged than the one that will be accumulating around the caps which they are giving you. So that one is pure. But there's that thing that we are drinking is not pure water. In fact, when you are drinking it, you should even be pecking it. I saw one video that there was a worm moving. I don't know if you saw that video, moving in a sachet water. So please don't buy ice water and start tearing and start drinking it. Check this in the content.
Okay, sir.
That is.
But, sir, even the one that you just said, sometimes you buy the sachet water, and then you see that the water has reacted with the rubber, so they become very, very slippery.
Yes. So
in that case,
why
is it the
we call it talit. Talit. So we have a paper on that. If you Google my name, so we call it talit, and this is coming from the production house to the sun, and then to the rubber production, they produce it with talate, melamine, and those kind of. So once it's exposed, it gets into the water, reacts with water, then it changes that. So if you look at the process from the factory to the production, the distribution, phthalates are released into the sachet water that we are drinking. And the phthalate can cause cancer, the cancer producing agent. Typhoid, cancer, and those So that's some research. So we did a survey where we collected water from almost the country, from the North Basin and everything, and then we're analyzing the phthalate content in that. You can Google it, and then we realized that most of our sachet water is coming from phthalate. We have phthalate in them, which is cancer agents. And we store them, most of them, you see them in the sand. So the bottled water can also release that when it's exposed to the sun for quite some time. It releases the phthalate in the rubber to react with that. Okay, so at least you should not be kind of going for any water if you are not sure of where it is coming from. And then the rubber which is also used, you should also be cautious of that as well. And that is that. I don't know why we can't, as at that time, as at this point, the country cannot produce a safe drinking water in our homes. That we should be buying sachet water and bottled water and then use the one that is coming from pipe water, Ghana water, water just to cook and then to bath. We can't drink it. I don't know why, but we are living in a country. So let's and most
It's because of Galamsey.
well, you see, the Galamsey, if your brother or your sister is doing some, you encourage it. If he's not doing that, you say that it is bad. Because I know of a family member who have taught for almost 20-something years. He has been renting all this while. Just 3 months in Galamsey. Here in Cape Coast, there's a town called Sweti. He has bought a house there just within 3 months. So he has stopped the teaching. He has taught 20-something years. We're just because 3 months. So if your brother is doing that, you will say that is good. So now we are encouraging him to even do more and bring money. It's quite funny. Let's move on. It's quite funny how we are doing what we are doing. There's no future for this country if we continue in that tangent. We are just wasting ourselves, and we are all part of the problem. Like what I'm teaching now, it's more theoretical something. Now, the practical of it is so simple, but then how do we do the practical? There's no practical part of it because it's going to cost us, and the country is not ready to go in that. So we'll just do the theory. Maybe when you grow and become the high top politician, you can do the practical for us. Okay, so calcium. So we are looking at the compounds of calcium like chalk, and chalk basically is a calcium carbonate. What we call the marbles or the limestone, calcite is just the same thing, calcium carbonate. Now I think now we don't use chalk a lot because of markets. I don't know if classrooms are still using chalks. I'll be surprised by then. Maybe in the rural areas, I am very sure. But then it's fading off gradually because where we were mining, and these are rocks, calcium carbonate are just rocks. So they just mill it into powder, use the calcium, just calcinate it, add some colors to just give it different colors. And that we use that. So we have the dunamite. So you see magnesium carbonate and dunamite is just the same as for the ore for calcium carbonate as well. Then the calcium sulfate, the ginseng, the calcium fluoride, the fluorides, and then the calcium oxide, which we call the quicklime. Okay, quicklime. That's a calcium. Now the fluorides can be in forms of what we call apatite. So we have the fluoroapatite, then we have the hydroxide apatite. Now these are the calcium-related compound that deposits on our teeth. Now again, we understand that our teeth is calcium and few magnesium, which forms that structure, that strong structure that we are seeing there. Now in our tongue, where the saliva, because we have calcium in there, we have some calcium in the mix in water. So saliva basically is calcium water mixture and some few proteins in there. So calcium is a good binder. So I remember those times when your paper gets torn, you just use your saliva to put the two papers together. Because calcium is a good binder. Yes.
Yes, apart from the formula of the quicklime and limestone, what's the other difference between quicklime and limestone?
I mean, you can see from formula base, quicklime is calcium oxide, and then limestone is calcium carbonate. Or you can't see.
I can see, but from the examples there, the chalk and the other quicklime down there, it's almost look the same.
What do you mean by it looks the same? Is it the name or what are you trying to say? I don't get it.
What I'm trying to say is that when you look at from the slide.
Yes.
But the one in the palm is the quicklime.
Yes. You mean the physical kind of observation?
Yes, sir. Yes, sir.
But then they are chemically they are not the same. I get you. So let me see. So in terms of that, this is a chalk. Okay. Yes, but then it's not the same as that one. In chemical composition, this is calcium oxide, this is calcium carbonate. Okay.
Say.
Yes, sir.
Yes.
Hello, sir.
Yes, sir.
Please, last time I got on ash, the wood ash, like teaching binary compounds. So and then they said wood ash contains some amount of calcium oxide.
Yes, right. It contains potassium hydroxide, calcium oxide, other kind of oxide related compounds. Yeah. So what's the question?
So my question is that if you take the wood ash, is it possible that you can separate the calcium oxide from it? Let's say, can you separate it?
Yes, I'm not. If you want to, they are all soluble in water, so I'm quite skeptical how you can separate them, because you are going to be dissolving them. Once you dissolve it, you have calcium, all the calcium moving to outside, then you leave the others also there. So I'm quite. I have to check if there's a way you can separate the wood, because not only that, it has all other compounds there. Okay, so when you burn an organic compound, you are going to be producing the carbon dioxide, well, carbon monoxide if it is not completely burnt, but carbon dioxide and water. In that water, we have other elements or other compounds that will be still remaining in that water, those soluble compounds. Okay, so the ash basically is just combination of other, just as you have mentioned. So if you dissolve it in water and they are all soluble, I'm quite, I want to understand how you can just say that I'm separating, for example, quicklime, then I'll separate sodium hydroxide, I'll separate that without having to go through the solution. I have to check though, and then I'll find out if you can just without, what I'm just thinking is whether it will be solubility, using solubility approach, but that I'm not sure that will work.
So, the follow-up question is that, assuming you are teaching this and then you mention the calcium oxide, and maybe a student asks you if you can practically, and you don't have like the picture you are having, you don't have it, and then you show an ash to the child that it contains calcium oxide. Is it correct?
Yes, and it's also the same as saying that ash is also potassium hydroxide. That is also correct. It's just like you saying that this water contains magnesium. So you can use that water to represent that it's magnesium in water. The same way it's calcium in water, and it's just the same. But because it's just a mixture of compounds. So once it's sodium, potassium hydroxide, it's calcium oxide, and there are a lot of other things that we can also find in that ash. So once you present, but the details of that, combinations of compounds in there, individual compounds in there, you can't really separate that. But as a bulky one, you can just represent it for all the other compounds that are present. Yes, Paulaka.
Yes, sir. Sir, I want to ask, since we are learning about calcium, why, when you take this pineapple, which is very sour, in fact, you feel very uncomfortable with your teeth? I don't know whether it's because that person have a reduction of calcium or what caused that.
You mean what is it? But I'm very sure this is just a calcium reacting with an acid. Okay, so the
So,
pineapple should have acidic content which your teeth has been exposed, so the calcium is having that reaction in there. No, so let me that reminds let me continue. So the appetite is the layer that protects the calcium, what you call the element. It protects the teeth. It forms a layer that protects that kind of teeth, and then of course also protects the gum. So if you look at it, ideally calcium is white. So if you look at it clearly, our teeth should be white. And in the olden days where we're not having toothpaste, our teeth was white. Until these white people, I don't know why you should call them white. They brought in the flora, fluorine related, and fluorine is yellowish in color. So then our calcium, which is white, we find in our teeth, will form a complex with the fluorine, and that is what you call appetite, fluoroappetite. Okay, and that appetite is yellow. So ideally, an ordinary person is having a yellow teeth. There's no white teeth unless you have bleached your teeth or you have put some coating on the teeth. There's no white teeth as we speak. If you go to the dentist that was white teeth, they only give you a bleaching agent to bleach it, bleach the appetite on it, but that will affect your gum. Okay, or you coat it. They have a coat like those that they use on your fingernails. They'll brush and then coat your teeth. That kind of and that's because the calcium forms. So the toothpaste contains fluorine in that. Of course, the fluorine protects the gum, but then after that we can't wash everything away. But then we then forms a complex in that. That's why and calcium is a very good binder. So that's why when you eat, you don't get the debris out. With time, it will form this debris which fills the hole, the middle kind of the holes between the teeth. So you have this debris being filled in because of the food particles which was not kind of gone. You didn't wash them out. So they'll form that between the teeth and they become very hard. Sometimes you even think it's part of the teeth. It is not a teeth. Go to the dentist, they'll remove those debris out because of, and that's the calcination. And the calcium binds all of them. So ideally, after every food, you have to wash your mouth. Not like brush your teeth, wash your mouth. And I remember those times when we're using the hacks of plantain, and then those of us from the coast like Gambia, I was using the akakucha. And it was quite effective than using the toothbrush and this paste. And they are so smart, they realize that when we're using those with the charcoal, we're having teeth. Now they have come with a new kind of innovation that charcoal toothpaste, just to come and deceive us that there's no, but then if you read the content, there is a fluorine in there. There is yes, a fluorine in there. In fact,
are we saying it's not advisable to use the fluorine?
I'm saying the fluorine protects the gum, but then it stays there and form what you call fluoroappetite, which deposits on our teeth and makes our teeth yellowish in color. So the more you are brushing your teeth, the more your teeth becomes yellow. That's an implication. Yes, and that's they keep on evolving from that, and they are bringing in new products. My intention was drawn, and when I check it, it's true that you should not even swallow. Some came with the idea that when you brush, if you want to have a fresh mouth, then after brushing, don't wash your mouth. Swallow the paste. I don't know if you you've heard of that thing. But then if you take Quagate, and the inscription on Quagate says that immediately you swallow, resort to the doctor because that's poisonous. And I'm very sure you are aware that we have different grades we have the natural toothpaste, we have the synthetic, different grades. So you can see it from the tail of the toothpaste with black color, blue color, red color, and green color. They use it at the end. So every fact, because we are not reading terms and conditions, so we just buy them and then we start using them. We don't even know why they put the green color there, the blue color, the red color, and then the black color. They just will tell you from the factory when you have problem, you sue them, they'll tell you you didn't read the terms and conditions. So the green color means that they have some content of natural systems in there. The black is purely synthetic paste. So you can, after this class, you can check the various colors that you see at the end, the tail end of the toothpaste there. You can check, and then when you're buying, you know which one you are. So when you swallow, Equagrade to tell you when swallowed, consult the doctor because it can create a problem in your system. Yes, Angela. Angela, I think I saw I've seen your hand, but if you are not talking, then I can move on. Okay, so that's calcium and calcium related compounds. Now, calcium also aids in this what you call acidic rain. And of course, if that happens, we are looking at rain that contains nitrate and sulfate in them, and that it can really, damage our trees there. So rains that contain this sulfate and the nitrates, and then most of the times it's just initiated by the calcium that we have. So that's just that. Okay. Now, how do we prepare quicklime? How do we form calcium oxide? Well, calcium oxide is from calcium carbonate. That is limestone. So that's where physically when you are observing that, you think that they are quite the same. Okay, so the quicklime is more powder form, like wet, it has water in that, and then the stone is the calcium carbonate. So when it decomposes or breaks down, it breaks down to form the calcium oxide and then the carbon dioxide. That's quicklime. So again, quicklime, when it engages water, will produce calcium hydroxide. So that's the quicklime preparation. Yes.
Hello, sir.
Yes.
So is there any particular reason why you didn't use arrow but you use equal to?
Oh, please, I can change it. There's no reason why I can change it.
No problem.
Okay. I know you are chemist and you are particular about the meaning of arrows and what they mean. So 1 arrow, 2 arrow, backward arrow, equal to arrow. So basically what I wanted to use was the double-sided arrow, like a reversible reaction.
Okay. Yeah.
So 1 arrow pointing forward, 1 arrow pointing back. That makes it reversible. So it means that calcium oxide plus carbon dioxide can also form the calcium carbonate. That's what I want to write. So it's not actually equal to. It's a double sign arrows.
All right.
Okay.
Hello?
Yes, sir.
Yeah, sir, please. Reacting the calcium oxide and water, is it forming an aqueous calcium hydroxide or solid?
Please, I don't know why I keep on missing this thing. So it's aqueous.
Okay. Which is lime water?
Lime water, yes.
Okay.
Okay. So uses, of course, we can have vast uses of calcium, which maybe you can take time to just go through. But most of the times, the ending of it is where we use more of the calcium because we have a lot of them stored in our bones, and then some also in our kidneys, so that we can help us excrete urine so easily. Some in our thyroid gland, we have calcium there. In our bloodstream, we can have calcium related also there. So it's quite kind of very vast. We use calcium in paint, in plastic production, in cosmetic, in wax, that's a crayon that we produce. We have calcium, anything that has a binder in that. Glasses, we have calcium oxide as glass, basically silicon dioxide, calcium oxide, and sodium oxide. That's what we call glass. When it's heated more than 1600 degrees Celsius, it melts, and then the sodium oxide is a clear kind of, it makes it clear. Calcium binds it. And so that's a sand that has melted and gives us what we call glass. And then they can change it into tubes or the flat surfaces, and then import for us to change it to various shapes. Okay, so that's calcium in there. So we have a lot of use for that. I want to
Hello,
finish.
sir.
Yes.
Oh, sir, sorry, you want to finish, but let me ask this question. Mostly there is is it clay or whatever the ladies have been eating? Whitish?
Yes. What's there? Especially when they are pregnant, there's that's
yes.
this. Yeah, so that's the quick line.
That's the quick line.
Yes. What's the local name? We call, I think Ayo for Ghans we call Ayo, but the tree, what's the name?
The fanciest we call it Shiro.
Shire or Shiro? Okay.
True,
Yeah, so Shire, yes. So that's the quick line.
So there is another one that is very flat, whitish, flat. That sometimes they use it to prepare medicine. Is it also contains calcium?
Well, I don't
know whether you have seen that.
I don't know. Maybe if you show me a picture, I can talk to that. A flat one.
Yeah, there is one B, very flat, like it's like a biscuit B type B. That it is also white. It's like
maybe after class, send me a picture and let me see. But what I know is that the market women, they buy the quick lime, add water to it, and then dry it. So they change it into various shapes and roll it, put some point on it, roll it, dry it, and then they go to sell. So people still eat that thing. Of course, I just think that it's just for taste. Tasting, but then I don't see any use for that. You are rather packing sand in your stomach, but the calcium part strengthens us. But I don't know the main use of that shit. And I still see people, because if you are passing like in Cape Coast here, Abra to Pedu to Abra, there is a place that they have a full table with that shit. I don't know which people comes to buy them. But then people are still selling, meaning people are also buying them. So I don't know specifically what they use it for. But in the olden times, I know that was what they were, pregnant women, and then those decoration for faces and those things, they were using these quick lines. But your biscuit type, I don't know what how it looks like. Maybe you can show me, and I can use it to upgrade my slide. Okay. Angela have raised her hand now, but I don't know if you don't have any question. Let me go to Strotium, and I can end
No, please.
there. Oh, then pull your hand down. Pull your hand down. Okay. Yeah, Strotium, which is having the atomic symbol SR. Of course, it belongs to the group 2. That's the alkaline earth metal, but that's very soft white. So normally we have to save that in paraffin oil. Very soft kind of metal. But we know Strotium to be having nice color. So just the 31st that passed, those fireworks that we're seeing are Strotium that were displacing for us to see those nice colors that were not the knockout, the one that goes into the air to just see that. Now we have Strotium ores like the Strotium, that's a Strotium carbonate, the sulfate, that's the celestine, the strontianite. That's the two common Strotium that we have. But in history, we know that if not for Strotium, we wouldn't have discovered what we call color TV. So we're used to have this cathode ray black and white. I'm sure those of you who are older can recall. Now we have moved from that cathode ray to it was the liquid or the liquid crystal screens. And now we are dealing with the diode, so the LCDs, and then now is the LEDs that we are now looking at. But then the colors of this thing that came was basically because we started noticing that strontium can form nice colors when we engage that. So that's where this cathode ray monitor started coming in. So they started using strontium for color TVs to give us the nice pictures that we have, because it has some magnetic kind of properties when combined with iron, and that gives us different flames when we combine it with iron, and that's where we kind of have this interesting, and of course that has graduated for us to even get to see that we can use strontium on our phone. So your screen that you are having, your smartphone that you are having, the screen basically is the colors you are seeing. The otherwise we're having the analog phones, the Nokia so and so and so. Because we started using strontium, then we started observing that we can have nice colors from that. However, there's a very harmful part to the use of strontium, and that it causes what we call the deleterious. And deleterious is quite even serious than somebody who smokes. So the effect of strontium, that is, if you stay on your phone for quite some time, it can affect your behavior. So research now shows that parents that give their phones to their kids, makes their kids become aggressive, and that's they even distort their kind of natural living. So if you are the type that always give your phone to your kid, if you take the phone, you see how that kid becomes quite aggressive and want to cry, want to create problem, distraction there, and those kind of stuff. And that's the strontium deceiving the brain. And it's what we call the deleterious effect. And for parents, or for adults, it also affects your sleep and your health. It can affect your social life as well. So we should be quite kind of very careful. Now, I want students, especially, I don't know if you can see my cursor. If you visit somebody who is having this decorated room, don't go there. Especially when you are a lady and you visit a guy and then he has this room, don't go there. It's a dangerous room. Those blue lights and those colors lights, don't go there. If you're a lady and go to a man's house, you see that. But this strontium gives nice colors, but then it can affect the eye as well. So it kind of deceives the eye and makes you colorblind. At a point, you will not be recognizing colors properly when you are exposed to it so much. And apart from the radiation, which we know that when we are sleeping, we don't put phones closer to your brain. I'm sure you are aware of that. So
Yes.
no wonder when you are sleeping, you'll be dreaming a big snake chasing you. These are radiation infected dreams. You'll be fighting in your dream, and then you wake up, you become weak. This is just the effect of phone. Not any spiritual. I'm very quite surprised where for us black man, everything is superstition. Hey, and then my come dying, I fought in my dream. I've conquered them. My friend, it's just your exposure to strontium. Be careful. Be careful. It's not. It's a devil. Okay. But however, we use strontium somehow to correct bone effect. So osteoporosis can be corrected when we have this strontium retinal. So it helps us to correct some of these bone stuff. Now, we have even come to the point where we see that strontium don't really react with our systems. So these metals that you see that they use in connecting, especially accident. Now, first, when you have an accident and you have a broken bone or something, they'll just amputate that part. But now they use these combinations of this polymer. We call them smart materials in dealing with you, and then your bones can connect back, and then they remove that from that as well. And that's now it's quite orthopedic surgery is now very expensive. Please be careful you don't find yourself in that in that situation, because just one surgery, the minimum you can hit is not less than 20,000. I can promise you, just at least orthopedic. And this time is cash down. If you don't put it down, they will not do it. So if you have an accident and if you have experience that, you can share your story, and that is quite disturbing. But that is a smart materials at play there. But in a nutshell, what we know scrotium to be is just the nice colors that we get to have from the fireworks as well. I just want to mention barium,
There.
and yes.
So can we say that the flame that comes out of the knockout, is it from strontium?
This flame, knockout is not knockout is basically is a carbide, which has been yes, but the sound. No, so we have fireworks and then we have knockout. It's not the same. But of course, we are calling everything knockout. But then the ones that fly into the air and give you nice colors, these are fireworks.
Oh, okay.
And the knockout is the one that knock out. It makes noise, boom, 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 boom. That's the knockout.
Some of them can give you this colorful thing, and at the end of the day, it will give you the blast.
No, means that it makes fireworks. So the fireworks flags, so it will bend to release the fireworks. Then the fire will then attach itself to the sound, and then you hear the sound. And it's quite common in outside. I think at the point there was this fire. So Ghana banned the use of these fireworks, but later it's gradually getting into the country again. Okay, so that's fireworks. And for example, if you get to have this green, nice fireworks, that is barium. Barium gives you nice greenish color, and that when it gets into contact with fire, it sparks and then it gives you nice barium. But we have barium used in paint, in bricks, in tiles, glasses, and then water as well. The common barium compounds that we have are the barium carbonate, barium sulfate, the barium chloride. These are the common barium compounds that we have. But then we should note that barium sulfate, the barium carbonate is toxic, but the sulfate is non-toxic. So we try to use that in treating, for example, X-rays. We have the barium sulfate. It helps us to track and see whether which we have that. And what I'm showing here is what we call the stones. So like a lead sulfate building up to become like a stone, blocking your digestive system, packing up. So you can see on this part, the stones are building up. It's getting to the upper part of it. And that's when it gets. So we can use that to track and then see that as well. Okay. Well, I think we agreed that on Friday we'll be meeting again. Sorry for yesterday. The rain cuts our lights here on campus, and so I couldn't meet you yesterday. But then I think coming Friday, if all things being equal, we can equally meet.
Yeah. Hello, Doc.
Yes.
Yeah, please. The slide, I'm not having them.
This is code, three of us.
It's true.
It's true.
Is this switch or code? Which one?
This switch.
Okay. So thank you for the reminder. So If it is Swish, then I'm going to send you this material. If it is code, then you are not under my umbrella. So please, if you have a platform or a group, you can just join, or if you want to take and share it to your platform. If it is Swish, then I am the coordinator. I should be able to give you the material.
Yeah, that is Switch. Switch. So,
Yeah, so
we have it. We have it long time ago.
you have it.
We
Maybe
don't
the
have it.
other.
We don't have
Yeah.
it. The
We
one
don't
that we
have
have
it.
is
Oh.
different.
we don't have it.
So
Too.
yeah, so
I
I'm the
have
coordinator. I need to
I have
send it.
all the materials.
And so then share it for them. If you have it, share it for them.
Please, sir, can we get
Okay.
the other questions?
Yeah,
Yeah,
yes, sir.
so if you have a group, and I was misplacing, I thought I'm teaching code. So if it is code, that one, the coordinator is quite different. So switch there, I'm the coordinator. So I'm going to be sending you all the material. So I have set of tutorial sets. These PowerPoint that I've prepared, and then some kind of materials, books that I have. I can drop them if you have a platform which I should be sharing it.
Yeah, so please, we have a platform, so we want it to be dropped there.
Okay.
Yeah, so please just notify me. You know my WhatsApp, just notify me. And then I'll just drop.
Ato,
Yes.
Ato,
Yes.
shall I collect then drop it?
Yeah.
If Ato is also because I gave it to the other kind of centers. So if Ato maybe is having, you can drop it.
Yeah, but we need the questions and other
Yeah,
materials.
so for that I can generate some for you. So if
Okay.
you have this material, I think for the other centers I gave them up to borrow. And I'm supposed to, I have the complete notes here, but I intentionally give the tutors up to borrow. So some of you, once you get the full material, you don't attend classes. So I intentionally give it as a part of it, so that after that they will give the rest. So I thought if you can contact me, I can then give you the questions involved and then whatever.
Yes, sir.
Yes, sir.
We even have a group for only this course.
Yeah, so that will be okay. So let's
Online
meet on.
sentence mail group.
So we
Yeah.
are meeting 2 days in a week so that I can make up the time. So today we've done the 3 hours more than that, but then so I can make it because I think it's 4 hours a week, right?
Yes,
Yes,
please.
sir.
Yeah, so
Yes,
at least 5 hours a week I can make it. I can make it.
Hello,
Okay,
sir.
so yes, sir.
Please, will we do practicals of this course?
No, please.
Oh, okay.
That will be next generation.
No, we have practical, which is a 207, and the 207 is a combination of this one, inorganic chemistry, and then a physical chemistry. So you'll be doing practical chemistry, which is a physical chemistry one. Is that correct? Practical physical chemistry.
Yeah, okay.
And that will entail inorganic and physical altogether.
Okay.
Okay.
Yes, but we don't have specifically like main group practical. No.
Okay.
Okay. So I see you. So please, the one in charge, if you can send me hi, I can get your contact and then I can start dropping materials if possible. Okay. So
Yes, sir,
see
my
you.
son won.
Okay. So see you.
Okay, so now there are two main group in one.
Yeah,
Online
Mate.
sentence main group chemistry.
Yeah.
After your Nintendo,
Is it tutorial questions now the pediatric because course name
And yeah, easy. That is what you want to.
Please, so I want to make some inquiries.
Please try and
This
contact me.
particular course, data collection and analysis, is it a call to everyone or to only particular people?
I guess it's a general course.
Please.
It's general for all physics, chemistry, biology.
No,
No.
please, from our portal, we don't have that
So,
course as part of our major chemistry and minor phases. Or
Okay.
machine
I'm doing
learning,
minor
and
biology. Maybe it's for
but no, for phases we don't have that course. But maybe biology people they have it.
okay. So this particular block, the physics people, you are doing how many courses?
We are doing 4.
Okay. We are doing 5. All right. Then I
Oh,
understand.
all right.
Thank you.
Okay, for
Okay.
our contact you. Okay.
Okay, let's see.
Okay.